Hello there, and welcome to Science for Sleep, where curiosity settles in beside you like a quiet companion, and science moves at a pace gentle enough to follow even with tired eyes. Tonight, we're wandering into one of the strangest regions ever discovered in the universe, a place so vast and so empty that even astronomers who spend their lives gazing into darkness found themselves stopping to wonder what they were looking at. It's called the Giant Void, and despite the dramatic name, it isn't the kind of emptiness that comes from forgetting something or misplacing a planet. It's a real region in space, unimaginably large and surprisingly quiet, a place where galaxies are rare, matter is scarce, and the usual busy structure of the cosmos seems to pull back and make room for something else. Before we go any farther, I'd love to know where you're listening from tonight. Maybe you're settled at home with a soft light nearby, or perhaps you're curled under blankets with the day finally slowing down. What time is it in your corner of the world right now? It always fascinates me that people spread across so many time zones can meet here for the same quiet moment at once. If you find this exploration soothing, or if it helps you unwind after a long day, I'd be grateful if you'd like the video or subscribe to the channel. It helps more sleepy explorers find their way here, and it tells me you'd like more gentle science to drift along with. With that said, let's begin easing our way toward this curious place in the universe, not with any rush or urgency, but with the same steady pace you might use while walking through a museum late at night, when the halls are empty and the echoes are soft and unhurried. There's something fitting about approaching a topic like this slowly. After all, the Giant Void isn't a place that reveals itself quickly. When we talk about space, we often imagine it as a vast emptiness, an expanse stretching in all directions with scattered stars and swirling galaxies. And in a broad sense, that's true. Most of space is empty if you measure it by the standards we use for everyday life. But when astronomers look at the universe in a structured way, they see that it isn't just a random scatter of stars floating in a featureless backdrop. It has patterns, connections, and shapes on scales so large our minds have trouble keeping them all in view at once. Galaxies gather in clusters, clusters connect into filaments, and those filaments weave a gigantic network that resembles a cosmic web. The spaces between those threads are what scientists call voids. These regions aren't absolute nothing, but they contain far fewer galaxies and far less matter than the surrounding areas. They're the low-density pockets of the universe, the quieter neighbourhoods in a cosmic city that stretches for billions of light years. Most voids are large, but still have a few galaxies scattered throughout them. They're like towns with long empty roads and a few houses spaced far apart. The Giant Void, however, doesn't follow the usual pattern. It stands out not only for its size, but for how little it contains. Even by cosmic standards, it seems to be more empty than expected. To get a sense of why that matters, it helps to picture the universe as researchers map it today. When astronomers create three-dimensional surveys of galaxies and plot them in space, they see clumps, strings, knots, and tunnels. It's one of the most remarkable discoveries of modern cosmology, that the universe has a kind of structure to it, shaped by gravity and influenced by the distribution of matter after the Big Bang. Most of the cosmos looks like spongework on an unimaginable scale, and within that intricate pattern, the Giant Void appears like a wide, quiet region, where the cosmic web thins out more than usual. When scientists first noticed it, the observation was met with curiosity, hesitation, and a little surprise. Not because voids were new, but because this one seemed too large and too empty to sit comfortably within the predictions of certain cosmological models. It wasn't simply an area with fewer galaxies, it was an area with far fewer than the model suggested should exist in that volume of space. That discrepancy raised questions about whether the standard understanding of cosmic evolution was complete, or whether this region might represent a rare but not impossible outcome of how matter settled, stretched, and clumped through cosmic history. But Before diving too deeply into that, it's important to appreciate how astronomers detect and map such enormous regions in the first place. Unlike taking a photo with a camera, mapping something billions of light years wide requires connecting observations from many angles and wavelengths. Some surveys look at the positions of galaxies directly, noting where they cluster and where they thin out. Others look at temperature patterns in the cosmic microwave background, which is the faint afterglow left over from the early universe. These temperature maps contain slight irregularities, tiny variations that reflect how matter was distributed long ago when the universe was still a dense plasma. These subtle variations are fingerprints of early structure, and over billions of years, those early differences grew under the influence of gravity. Denser regions accumulated matter and formed galaxies, while less dense regions expanded into voids. When astronomers compared the maps of galaxies with certain cold or warm spots in the microwave background, they began to notice correlations. One of these correlations led to the suspicion that an unusually large void might be responsible for a certain temperature anomaly. That connection didn't prove anything by itself, but it encouraged scientists to take a closer look. The closer look revealed something unexpected. A region roughly 1.5 billion light-years across seemed to contain far fewer galaxies than anticipated. Even at the lower density typical of voids, this area stood out dramatically. It wasn't completely empty, but compared to surrounding regions, it was noticeably sparse. The question that followed was straightforward. How could such a structure arise? Was it an example of a natural extreme within normal cosmic evolution, or did it indicate something more unusual? As scientists debated those possibilities, the giant void gained attention not only for its size, but also for its potential connection to deeper cosmological questions. Some researchers wondered whether it could be tied to dark energy, the mysterious force driving the accelerated expansion of the universe. Others speculated that it might reflect variations in the distribution of dark matter, the invisible substance that makes up most of the universe's mass. Still, others considered whether the void might simply be a rare fluctuation that happened to appear in one of the regions we've examined in detail. This ongoing discussion continues today, with new surveys and techniques gradually refining the picture. To understand the implications, let's consider what a void really means in practical terms. In everyday life, an empty room might feel quiet and still. In astronomy, an empty region means fewer galaxies, less matter, and fewer gravitational influences pulling on surrounding structures. The presence of a large void can affect how light travels through that region, causing subtle distortions in measurements of distant sources. These distortions must be accounted for when estimating cosmic distances, analysing gravitational lensing, or studying the distribution of matter on large scales. So, finding a void as large as the giant void isn't just a curiosity, it's something that shapes multiple kinds of observations. That means understanding it isn't optional for astronomers hoping to build accurate models of the universe. The giant void influences measurements taken from Earth, from space-based telescopes, and from cosmic background detectors. Ignoring it would be like trying to map an ocean while pretending a particularly large and deep basin didn't exist. For listeners settling into sleep, the idea of an immense empty region might seem strangely calming. It's almost counterintuitive that emptiness on such a scale could feel peaceful rather than unsettling. But in the context of the universe, emptiness isn't a mark of absence, it's part of a natural pattern. The cosmos evolves by clustering and separating, forming dense networks and spacious regions. Emptiness is as essential to this structure as the galaxies themselves. And when we look at it in that light, the giant void isn't a flaw in the universe or a break in the pattern. It's a feature, one that took billions of years to develop and stretch into its current shape. Even though it's easy to feel small when thinking about something so large, there's also a kind of perspective that can be found in contemplating it. Our everyday concerns, schedules and routines unfold within a tiny corner of one galaxy, which is itself a small part of the cosmic web. And yet here we are, able to learn about something billions of light years away. something that challenges our understanding of how matter arranges itself across the universe. That ability to observe, question, and analyze is one of the most remarkable things about being human. Even at the end of a long day, with thoughts drifting and eyes growing heavier, the fact that we can contemplate structures so immense and so distant speaks to the power of curiosity and the steady progress of science. When we picture the universe, it's tempting to think of it as a canvas of scattered points against an endless backdrop, small lights in a wide dark space. That image isn't wrong, but it leaves out some of the most important features of how everything is arranged on the larger scales. The universe is far more structured than it appears at first glance, filled with layers and patterns that only start to make sense when you zoom out far enough. What we usually call space, that dark expanse between stars, carries its own kind of complexity. Even emptiness is not evenly spread. There are dense regions filled with galaxies and clusters, and then there are places where the usual presence of matter grows thin. Understanding why some regions teem with activity while others remain quiet helps reveal how the cosmos has evolved since its earliest moments. To understand why these differences exist, it helps to step back and look at the universe not as a place defined by its objects, but as a system shaped by gravity acting on the earliest fluctuations in matter. After the Big Bang, the universe was hot, dense, and nearly uniform, but not perfectly so. Tiny variations in density existed, incredibly small at first, but they mattered. Over billions of years, those small differences grew. Regions that were slightly denser attracted more matter and became even denser, eventually forming stars, galaxies, clusters, and massive walls of structure that stretch across enormous distances. Meanwhile, regions that started slightly less dense shed matter to their neighbours and gradually grew emptier. Over time, these differences amplified until the universe developed a complex network of filled and unfilled spaces. The filled regions form the cosmic web, while the unfilled ones form the voids. Even though these concepts feel abstract, they come from observations that are very specific. When astronomers build large surveys mapping galaxies in 3 dimensions, the structure emerges almost immediately. The data doesn't scatter randomly. It organises itself into threads, sheets, and knots that outline an immense lattice of matter. Inside this lattice are the gaps, and those gaps are not mistakes or leftover spaces. They are essential parts of the network. They influence how the filled regions form, how matter flows, and how galaxies grow. If the universe didn't have these empty regions, the cosmic web itself would not develop the way it does. One of the surprises that emerges from studying the cosmic web is how much the universe is actually filled with something when compared to its supposed emptiness. Every dot in a survey represents a galaxy containing billions or hundreds of billions of stars. Every filament connecting galaxies is drawn together by dark matter. Every cluster is the result of gravitational collapse happening on a scale far too large to imagine through everyday comparisons. Even the expanses between galaxies, what we casually call empty, contain particles, radiation, magnetic fields, and the invisible influence of dark energy driving cosmic expansion. True emptiness, in the strictest sense, does not really exist in the universe we observe. There is always something, even if that something is thinly spread. Yet within all that something, there are regions where that presence thins out dramatically. These areas are not errors or gaps in understanding. They're places where the density of matter is lower than average, where the cosmic web loops around a volume rather than running straight through it. These regions are known as cosmic voids, and they differ greatly in size and shape depending on how matter settled during cosmic history. Some are modest, just tens of millions of light years across. Others are enormous, stretching hundreds of millions of light years. And then, very rarely, there are supervoids that extend across regions so vast they challenge expectations about the universe's structure. The giant void falls into this rare category. Before focusing on that particular location, It helps to appreciate what makes these empty regions interesting beyond their lack of matter. A void isn't merely an absence. It changes how gravitational forces distribute in the surrounding areas. It affects the motion of galaxies near its borders. It influences how radiation passes through it. It even shifts how we measure certain cosmological parameters, because the universe is not uniform and measurements depend on which paths light has taken. When a photon from a distant galaxy travels through a void, the journey isn't the same as if it passed through a dense cluster. The gravitational landscape differs. Light can lose or gain energy in subtle ways. These effects must be taken into account when building large-scale maps of the cosmos. Another reason voids matter has to do with how they formed. When scientists try to simulate the universe on massive scales, they begin with conditions inferred from observations of the cosmic microwave background. These simulations run forward in time, allowing gravity to shape matter into the cosmic web. If the simulations match what we see in the large-scale structure, it suggests that our understanding of cosmology is on the right track, and for the most part, simulations do reproduce the overall layout. Dense nodes emerge, filaments connect them, voids appear naturally in between. The consistency between theory and observation is one of the triumphs of modern cosmology. However, even within that match there are statistical expectations. Some voids should be large, others small. There should be a distribution of sizes shaped by the early differences in density. Most voids should fall within a predictable range. When a void stands out, when it is significantly larger, emptier, or differently shaped than expected, it raises questions. It doesn't mean the model is wrong, but it suggests that something unusual has occurred within that region's history, or in the density fluctuations that shaped it. The giant void is one such case. It fits into the overall picture of cosmic structure, but sits at one edge of the distribution, where the largest and emptiest voids rarely appear. Even before the giant void was identified, astronomers recognized that voids were not simple. They contained faint galaxies, streams of matter, and occasional isolated structures. They weren't entirely silent. Some galaxies within voids behave differently from their counterparts in crowded regions. They can have unusual shapes or slower rates of star formation. They might evolve under different environmental pressures because they don't have as many neighbouring galaxies influencing them. These details help paint a picture of cosmic diversity. Not all galaxies grow in bustling neighbourhood clusters. Some grow in isolation, shaped by quieter surroundings. This environmental difference stretches all the way to the dynamics of the universe. In denser regions, gravity pulls more strongly, light bends more sharply, galaxies interact more frequently. In voids, the opposite is true. Gravity is weaker, interactions are rarer. The pace of evolution differs. By comparing these different environments, scientists learn not just how galaxies form, but how the universe matured from its earliest moments. Each region, filled or empty, contributes something important. The interesting thing about these differences is that they create a kind of tension between what we intuitively consider full and what we consider empty. A void isn't nothing. It's still part of the universe's behaviour, and a dense region isn't everything. It's just one part of the network. When you take both sides together, the structure makes sense in a way that neither would alone. The universe isn't a random scatter. It's a balanced system where matter gathers in some places and retreats in others. That's why the giant void stands out. It represents a region where matter retreated more dramatically than usual, creating a space that, on the scale of the cosmos, feels unexpectedly quiet. But before reaching that specific location, it helps to understand how scientists first recognized such quiet regions were part of the cosmic structure. It wasn't always obvious. The earliest maps of the universe were incomplete. At first, astronomers could see only the bright nearby galaxies. The more distant ones were too faint, and the distribution looked uneven. As telescopes improved and larger surveys were compiled, patterns emerged. What looked random in small samples became structured in large ones. With each expansion of our observational reach, the cosmic web came more sharply into focus. The realization that the universe was structured in this way was a turning point. It meant that emptiness was not a background, but an active participant in the shape of everything. It also meant that astronomers had to consider not just the luminous matter they could see, but the invisible matter inferred from gravitational effects. Dark matter played a major role in shaping the cosmic web, guiding how galaxies formed and where voids emerged. Without dark matter, the structure would not look the way it does. The interplay between matter and emptiness became a central part of cosmology, and voids became just as important to study as clusters. Even though voids are not as dramatic visually as galaxies or nebulae, they hold significance for another reason. They are sensitive to certain cosmological parameters. The rate at which voids expand and their typical sizes help test theories about dark energy. The way matter flows around them reveals information about gravitational behaviour on very large scales. If a theory predicts the wrong number or shape of voids, it has to be revised. This makes voids a kind of testing ground. They help fine-tune our understanding of how the universe's expansion changes over time. In practical terms, that means astronomers regularly revisit voids with new data. They compare maps from different surveys, check them against simulations, and refine their descriptions. With each round, the structure of the universe becomes clearer. The giant void, which remains unusual even in updated surveys, serves as a reminder that not every region fits neatly into expectations. Some areas challenge models and encourage new investigations. Thinking about these differences, full regions, empty regions, and the balance between them, can give a sense of how dynamic the universe is, even on scales far larger than a human lifetime or a human world. The universe isn't static. It expands, stretches, and evolves. Structures grow, merge, and change shape. Voids widen as matter flows outward. Dense clusters grow heavier. Every piece of the cosmic web is moving in response to the forces shaping it. Even the emptiest regions are part of that motion. When astronomers began charting the universe in greater detail, they weren't looking for anything like the giant void. Their goal was simpler: to understand how galaxies were arranged across enormous distances and to see whether the structure of the cosmos matched what theories predicted. At the time, many of the earliest large-scale surveys were limited by the technology available. Telescopes could only capture so much at once, and the distances to far-off galaxies were difficult to calculate with precision. Yet even with those constraints, researchers noticed something unusual as they expanded their maps. Some regions looked busy and bright, while others seemed surprisingly thin. Those thin regions were not immediately labelled as voids. They were simply areas with fewer galaxies. It wasn't until larger surveys were undertaken that the empty stretches began to reveal their significance. One of the moments that pushed astronomers toward a clearer understanding of these empty spaces came from efforts to measure the large-scale distribution of galaxies. In the 1970s and 1980s, new instruments made it possible to record not just the positions of galaxies on the sky, but their distances as well. Once distance information was added, the universe took on a three-dimensional shape that changed how everything looked. Instead of flat maps, there were deep cones of data that showed the layering of galaxies far into the universe. This gave researchers an early glimpse of patterns they had not expected. Filaments, walls, and hollow spaces. Some of these early results surprised scientists because they seemed too structured for a universe that had once been almost uniform. The discovery of the Great Wall, a vast filament of galaxies stretching across hundreds of millions of light years, hinted that the universe was not randomly clumped. But for every dense wall of galaxies, there were also volumes that looked unusually empty. At first, these empty pockets were interpreted as normal variations. After all, the cosmos wasn't expected to be perfectly even. But one pattern that kept appearing was the presence of large gaps in the maps. These weren't small emissions caused by observational limits. They were real regions with noticeably fewer galaxies. As technology improved, surveys became more sophisticated. The Sloan Digital Sky Survey, SDSS, which began in the early 2000s, was one of the most influential. It provided a dramatically detailed picture of millions of galaxies, charting their locations in three-dimensional space. When these data were converted into visualizations, the cosmic web became unmistakable. Dense filaments stretched like interconnected highways, while enormous voids opened between them. With each new slice of the sky added to the map, the web grew more detailed. And yet, something remained odd about a particular region. Before the giant void was identified by name, astronomers noticed an area in certain surveys where the distribution of galaxies dipped more dramatically than in neighbouring sectors. The decrease was not subtle. It created a patch that looked noticeably underpopulated. And while underpopulated regions were common, this one stood out simply because of its size. It was wide, deep, and less dense than expected. But spotting an unusual region did not automatically lead to any conclusions. Astronomers needed more than one survey, more than one method, and more than one confirmation before they could call anything significant. Part of what made the search for cosmic voids more refined was a shift towards studying not just galaxies, but also the cosmic microwave background. This faint afterglow, left from the early universe, carries tiny temperature fluctuations that reflect early density variations. When researchers compared these temperature fluctuations to structures in the modern universe, they noticed something interesting. In some areas, the temperature of the microwave background appeared slightly colder or slightly warmer than nearby regions. These temperature differences could be influenced by something known as the integrated Sachs-Wolf effect, in which the gravitational potential of large structures affects the energy of passing photons. In simpler terms, if light from the early universe passes through a very large void or a very dense cluster, it can be shifted in a measurable way. One particular temperature anomaly caught attention. It was an unusually cold region in the microwave background, often referred to as the CMB cold spot. At first, the cause of this cold region was debated. Some suggested it might be a result of statistical fluctuations. Others wondered whether there might be something in that direction of the universe affecting the photons. If a region large enough and empty enough existed, it could potentially contribute to a cold spot through this subtle gravitational effect. That raised a new possibility. Maybe the large empty region noticed in galaxy surveys and the cold patch seen in the cosmic microwave background were connected. This possibility prompted researchers to examine the area in greater detail. They looked more closely at galaxy distributions, examined redshift information, and studied density variations across different surveys. As they compiled the data, it became clearer that the region was unusually empty over an enormous volume. Other parts of the universe contained voids as well, but this one seemed to stand apart in scale. What began as a curiosity, a slightly thinner area on a galaxy map, started to look like a feature worth naming. That feature became known as the giant void. One interesting aspect of this discovery is that no single observation declared it outright. Instead, it was a gradual accumulation of evidence. Each data set revealed a little more about the region. When combined, those pieces formed a picture of a large, low-density space that could not be dismissed as a normal variation. Its size, its position, and its connection to other observations made it a subject of active research. Astronomers wanted to know whether it was truly exceptional or simply at the upper end of what cosmic structure allowed. Part of the investigation involved checking the consistency of distance measurements. Galaxies far away do not always appear evenly in surveys because of selection effects. Some galaxies are too faint to spot at certain distances. Others are too redshifted for certain instruments to detect. But even after correcting for these observational limitations, the region still appeared emptier than expected. That reinforced the idea that the void was real rather than an artifact of an incomplete survey. Another point of interest was how the surrounding structures behaved. If a large void existed, it would influence the motion of galaxies around it. matter flows away from underdense regions and toward overdense ones. This process, known as gravitational flow, shapes how galaxies drift over time. By studying the velocities of certain galaxies near the boundaries of the void, astronomers hoped to see whether their motions aligned with expectations for such a vast underdensity. The findings were consistent enough to add weight to the interpretation. The region was not a minor variation, but a substantial structure. Even with these confirmations, astronomers continue to compare the void to simulations. Large computational models of the universe use physics from the Big Bang onward to predict the formation of galaxies, clusters, and voids. When these models are run repeatedly with different initial conditions, they produce distributions of void sizes. Most simulations predicted a certain number of large voids, but extremely large ones like the giant void were rare. Not impossible, but rare enough to warrant attention. This raised a series of questions. Was the giant void simply a statistical outlier? Was it an example of a rare but permissible structure? Or was its size indicating something deeper about how matter distributed itself over cosmic time? None of these questions could be answered immediately. They required careful analysis, comparisons with other anomalies, and consideration of how dark matter and dark energy influence large-scale structure. Throughout this investigation, another challenge emerged: identifying the boundaries of the void itself. Voids do not have sharp edges. They gradually transition from sparse regions to more typical densities. Defining where one ends and another begins is not as straightforward as drawing a circle on a map. Astronomers use mathematical criteria to determine the density contrast between regions, but the definitions can vary. Depending on the method, the estimated size of the void can shift. Despite these uncertainties, the classification of the giant void as an unusually large underdensity held firm across different approaches. As more data arrived, the story grew more detailed. Surveys using infrared observations, which are good at detecting distant galaxies obscured by dust, found fewer galaxies in that direction as well. Radio surveys added more information about the presence of hydrogen gas. All these indicators pointed to the same conclusion. The region lacked the usual structures expected in that volume of the universe. For astronomers, stumbling upon this cosmic missing piece was not as dramatic as discovering a new planet or spotting a bright supernova. It was more subtle. It required patience, repeated observations, and a willingness to follow hints that were not immediately clear. The giant void did not announce itself loudly. It emerged gradually from patterns in data, revealing itself only when the maps grew detailed enough to show the full shape of the cosmic landscape. What made the discovery meaningful wasn't simply that the void existed, but that its existence intersected with other unsolved questions in cosmology. The connection to the microwave background cold spot, the implications for large-scale structure, and the rarity suggested by simulations all contributed to its importance. It became more than just an empty region. It became a clue. But clues in cosmology do not provide answers by themselves. They must be placed within the larger framework of the universe's evolution. When astronomers describe a void, the word can be misleading. In everyday language, void suggests emptiness in an absolute sense, a kind of nothingness without substance or structure. But in cosmology, a void is not a perfect absence. It is a region with less matter than average, often far less, but still not entirely empty. Even the most extreme voids contain galaxies, gas, dark matter, and radiation, just spread so thinly that the usual patterns of the universe fade away. Understanding what this means requires looking at scale in a way that does not come naturally. Most of the numbers involved are too large to picture directly, so the mind tends to reduce them to vague impressions. To make sense of the immensity of a void, it helps to build that picture step by step. A starting point is to consider the distance between stars in our own galaxy. The Sun and the nearest star, Proxima Centauri, are separated by about 4.24 light-years. That distance feels enormous, and it is, but in cosmic terms it's typical. The Milky Way contains hundreds of billions of stars, yet most of its volume is empty enough that light years can pass between neighbouring suns without anything in between besides thin gas and dark matter. This emptiness is ordinary, expected, and essential for galaxies to maintain their structure. Even crowded regions like the cores of galaxies maintain significant spacing between stars. If we zoom out further, the distances between galaxies themselves become far greater. And it's at these intergalactic scales that the concept of a void begins to take shape. In most regions of the universe, galaxies appear in groups, clusters, filaments, and walls. These structures span hundreds of millions of light years and contain enormous numbers of galaxies. Between them lie areas where galaxies are fewer and farther apart. These are the voids. A typical void might stretch tens of millions of light years in every direction, large enough that an entire galaxy cluster could fit inside with room to spare. And yet, within the cosmic web, these voids are not unusual. They form naturally as matter moves under the influence of gravity, concentrating in dense structures and draining away from less dense regions. The giant void pushes this concept much farther. Its estimated diameter approaches 1.5 billion light-years, making it one of the largest known underdense regions in the observable universe. To understand what that means, consider that the Milky Way is about 100,000 light-years across. The giant void is roughly 15,000 times wider. If the Milky Way were the size of a grain of fine sand, the giant void would span several kilometres. That comparison is imperfect, of course, because the universe doesn't scale neatly into objects we can hold in our hands, but it offers a rough sense of proportion, enough to show just how wide this region is. Even so, width alone does not describe the scale fully. The volume of a void expands as the cube of its radius. That means a void slightly larger than another can contain far more empty space. The giant void's volume is measured in cubic billions of light-years, a figure so large that it dwarfs any structures nearby. And within that volume, the density of galaxies drops far below the average. In typical regions of similar size, astronomers expect to find thousands of galaxies. In this void, far fewer appear. The difference is not a minor fluctuation. It is a major deviation from what would normally be predicted in such a volume. To visualize this, imagine the universe as a vast three-dimensional grid. Every point in the grid represents a potential location of galaxies. In most regions, these points light up frequently, indicating the presence of stars, gas, and structure. In the giant void, the grid would show mostly darkness, with only occasional faint points representing isolated galaxies drifting in a low-density environment. Those galaxies are present, but they are lonely compared to others. Their nearest neighbours are far away. Their evolution may have taken different paths because they grew without the usual influence of nearby galaxies. Even the concept of emptiness becomes relative when discussing cosmic voids. What counts as empty on one scale may not feel empty on another. In a human-built structure, an empty warehouse or an empty parking lot is easy to grasp. In the universe, emptiness means that a region has perhaps 10% or less of the average matter density. But the average density of the universe itself is incredibly low. Spread all the matter in the observable universe evenly, and each cubic metre would contain only a handful of particles. A void, by comparison, might contain only a fraction of that already tiny amount. It is a thinness beyond ordinary perception, but measurable through gravitational effects and galaxy counts. This thinness has consequences. One of the key features of a void is how its low density affects the expansion of space within it. Regions with less matter experience a slightly faster rate of expansion because they offer less gravitational resistance to the stretching of space. Over billions of years, this enhanced expansion amplifies the emptiness, pushing matter even farther from the centre and widening the void. The giant void, if it developed from an initial underdensity in the early universe, would have expanded more rapidly than denser surroundings, contributing to its immense size today. Understanding the immensity of a void also involves considering time. The universe has been expanding for roughly 13.8 billion years, and during that time matter has flowed away from low-density regions. If a region started with slightly fewer particles than average, the gravitational pull elsewhere would draw more matter out of it, deepening the underdensity. Over cosmic time, this process magnifies the difference. Small variations grow into large structures. The giant void reflects not just the structure of the universe now, but its entire history of gravitational evolution. Even though voids grow slowly, the changes accumulate over scales far beyond human experience. When astronomers simulate the universe's evolution, they start with a nearly uniform distribution of matter and let gravity act according to the laws of physics. Over time, the simulations produce a pattern of filaments, walls, clusters, and voids that matches observations. These models help to confirm that emptiness is not an incidental feature, but a natural outcome of gravitational dynamics. Yet in these simulations, the largest voids rarely reach the size of the giant void. Some appear, but not many. That rarity is part of what makes this particular void noteworthy. Another way to appreciate the immensity of a cosmic void is to examine the distances involved in crossing it. If one could travel at the speed of light, the fastest possible speed, it would still take over 1 billion years to traverse the giant void from one end to the other. That journey would pass through regions where galaxies are scarce, gas is thin, and the gravitational landscape is unusually smooth compared to denser areas. In a sense, it would be like travelling through a cosmic desert, where the usual landmarks of the universe grow few and far between. This smoothness affects how astronomers interpret light from distant objects. Light travelling through a void experiences different gravitational conditions than light travelling through a dense region. These differences can create subtle shifts in the energy of photons, affecting measurements of cosmic distances, expansion rates, and the microwave background. The void does not simply sit idly in space, it interacts with the light that passes through it. And because the giant void spans such a large region, its influence extends across many lines of sight. When discussing the immensity of a void, it's important to keep in mind that voids are part of the universe's structure on the larger scales. They are not separate objects or isolated features. They arise from the distribution of matter itself. The cosmic web is the result of billions of years of gravitational interaction, and voids are woven into that web just as filaments and clusters are. The giant void represents an extreme point on the spectrum, but it fits into the broader picture of how the universe arranges its matter. One question that often arises when thinking about voids is whether they can contain anything unusual. The idea of a region so large and so empty invites speculation. Could there be unusual forms of matter inside? Could dark energy behave differently within a void? Could unknown physics be hiding in the gaps? These questions don't arise from anything specifically observed in the giant void, but from the general nature of emptiness itself. Scientists explore these possibilities not because voids show obvious signs of unusual phenomena, but because voids offer a clean environment in which to test cosmological ideas. With fewer galaxies and less matter complicating the view, voids allow researchers to look for subtle effects that might be difficult to detect in denser regions. The immensity of a void also affects how galaxies inside it evolve. In dense regions, galaxies frequently interact and merge. These interactions can trigger bursts of star formation or alter galactic shapes. Inside a void, such interactions are far less common. A galaxy in a void may evolve more slowly, form fewer stars, or develop unusual features because it lacks strong external gravitational influences. Observations of void galaxies often reveal differences in their structure and composition. These differences are important for understanding how environment shapes galactic evolution. Despite the sparse nature of voids, they are not uniform internally. Some parts may be slightly denser than others. Small filaments may stretch through them. isolated galaxy groups may form in pockets. Even within the giant void, there are areas that contain galaxies, though they are few and widely separated. Mapping these internal variations helps astronomers understand how matter distributes itself at the lowest densities. It also helps refine models of how voids grow over time. Another aspect of voids that contributes to their immense scale is how they relate to neighbouring structures. A void does not exist in isolation. It sits within a network of filaments and walls. The boundaries between a void and the surrounding structures are not sharp. They are gradual transitions where density increases slowly. These boundaries can stretch for hundreds of millions of light years. The giant void, being exceptionally large, touches multiple filaments and sheets of galaxies. Its borders influence how matter flows along those structures, and the movements of galaxies near the boundary reflect the gravitational pull of the surrounding web. The immensity of a void can also be appreciated by looking at the number of galaxies missing from it, compared to an average region. If a typical volume of that size would contain several thousand galaxies, and the void contains only a small fraction of that number, the difference is significant. Each absent galaxy represents a portion of matter that gathered elsewhere, contributing to the formation of denser structures. The void is not just empty. It is empty because the matter that could have filled it is now part of something else. Understanding this balance helps clarify why voids are important. They are not just spaces between things. They are records of cosmic evolution showing where matter did not go. They help reveal how the universe's structure emerged from initial conditions governed by physics. And they provide environments where certain cosmological effects are easier to study. Another way to describe the immensity of a void is to consider how much space exists between the few galaxies inside. In a typical region, galaxies might be separated by several million light years. In the giant void, those separations can be far larger. A galaxy inside the void might not have close neighbours for tens or hundreds of millions of light years. This loneliness is not something galaxies experience in denser clusters. The difference shapes their evolution and offers insights into how environment affects galactic behaviour. The immensity of voids also becomes clear when examining how they affect bulk flows of matter. Matter tends to move away from void centres, creating large-scale flows that stretch outward. These flows can influence the motion of galaxies over enormous distances. When astronomers analyse the velocities of galaxies in certain regions, they must account for the gravitational influence of nearby voids. The giant void, due to its size, plays a role in shaping the motion of some galaxies along its boundaries. As observations improve, the ability to map voids becomes more refined. Surveys using different wavelengths, optical, infrared, radio, each contribute pieces of information. These data help form a more complete picture of the void's interior, boundaries, and surroundings. With each improvement in mapping, the immensity of the void becomes clearer. It is not just large in one dimension. It extends across a volume that defines an entire region of the cosmic landscape. Ultimately, understanding the scale of nothing in the universe is not about picturing a blank space. It's about recognizing that even emptiness has structure, influence, and history. A void grows not by being empty, but by being less filled than its surroundings. Over time, that difference shapes the universe's large-scale architecture. The giant void is an extreme example of this process, a vast underdense region that stretches across a significant portion of the observable universe. Its immensity reflects billions of years of cosmic evolution and the interplay of gravity, dark matter, and expansion. Moving from this sense of scale toward a deeper understanding of what typical cosmic environments look like helps place the giant void in context. The distribution of galaxies elsewhere, the formation of clusters, and the behaviour of filaments all contribute to the comparison that makes this void appear so striking. The contrast between the fullness of most cosmic regions and the sparseness of a void highlights how the universe organises its matter. By exploring those typical environments, the significance of the giant void becomes even clearer. The universe, for all its vastness, is full of familiar patterns once you begin looking closely enough. Galaxies are not scattered aimlessly across space. They gather, stretch, cluster, and connect in ways that reflect billions of years of gravitational movement. To understand why a void stands apart, it helps to first understand what most regions of the cosmos look like. In many parts of the universe, matter comes together in predictable, structured ways. These ordinary cosmic neighbourhoods form the majority of the large-scale landscape, and they tell us how the universe behaves when it has enough matter to work with. By seeing what fills those regions, how galaxies interact, how gas flows, how dark matter shapes the underlying structure, it becomes easiest to appreciate how unusual a place like the giant void really is. The most common environment in the universe is not the emptiness between galaxies, but the filaments of the cosmic web where matter collects. These filaments are long strands stretching across hundreds of millions of light years. They contain chains of galaxies pulled together by dark matter. The distribution is not perfectly even, but there is a rhythm to it. Galaxies appear in groups along these strands, much like towns along an ancient trade route. The material binding them together is largely invisible. Dark matter forms the underlying scaffold, pulling in gas and stars and guiding how each structure grows. These filaments are surrounded by other filaments, connected at great junction points where the largest galaxy clusters form. Clusters are among the most crowded environments in the universe. They contain hundreds to thousands of galaxies packed into regions only a few million light-years across. Within these clusters, galaxies do not remain separate for long. They interact frequently, the gravitational fields tugging on each other, distorting shapes, and sometimes throwing stars into intergalactic space. These interactions can trigger bursts of star formation, or halt it entirely, depending on how the galaxies collide. The environment is dynamic, full of movement and change. Gas clouds heat up as they fall into the cluster. Shock waves ripple through the intergalactic medium. Dark matter anchors the entire cluster, shaping the gravitational landscape. Outside these dense regions, galaxies still populate filaments and walls where the density is lower but far from empty. These structures form the backbone of the cosmic web. They carry gas along their length, feeding galaxies with the material needed to form new stars. They act like channels, moving matter toward clusters and away from voids. On these scales, the behaviour of galaxies is shaped by their surroundings. Their evolution is influenced by close neighbours, by the flow of gas, and by the motions of the larger structure. In ordinary regions, galaxies are rarely isolated. Even in relatively sparse areas of the cosmic web, galaxies tend to have companions within a few million light-years. They follow the gravitational contours of the dark matter that surrounds them, moving gradually toward denser regions. Their interactions may be gentle, but they still affect their shapes and development. Spiral galaxies may maintain their structure in quieter regions, while elliptical galaxies may dominate clusters where collisions are frequent. The environment determines whether a galaxy continues forming stars, or whether its star-forming gas gets stripped away by interactions with the cluster's hot medium. These environments contrast sharply with what happens inside a void. A void is more than just a space with few galaxies. Its emptiness changes the rules. Galaxies inside a void live quieter lives. They have fewer neighbours, fewer encounters, and slower evolutionary paths. But to fully appreciate the contrast, it helps to continue picturing what fills the majority of the universe, what most galaxies experience as their normal environment. If you were to map out the density of matter across the cosmos, most of the volume would fall into a middle range, not as thick as a cluster, not as thin as a void, but somewhere in between. These intermediate density regions are where galaxies like the Milky Way tend to reside. The Milky Way sits within a filament, part of a small local group of galaxies, which in turn belongs to a larger structure known as the Virgo supercluster. This web-like hierarchy is typical. Galaxies are not scattered objects. They belong to nested systems that reflect the gravitational history of the universe. Because these environments are filled with matter, they form the canvas on which the universe paints its structure. Gas flows along filaments, cools, and enters galaxies. Smaller galaxies fall into larger ones. Dark matter halos merge. Each step produces new layers of complexity. Over billions of years, this process shapes the luminous universe we see through telescopes. All of these processes, merging, flowing, heating, cooling, are the hallmarks of ordinary cosmic neighbourhoods. The differences between those regions and voids become clear when you consider the typical density contrast found in the cosmic web. If the average density of matter across the universe is set to a value of 1, dense clusters might reach tens or even hundreds of times that average. Filaments may be 2 or 3 times the average. Walls might be slightly above average. Voids, however, can fall to just 10 or 20% of the average density, sometimes lower. The giant void dips even further in some regions. That deviation is what sets it apart. Ordinary cosmic neighbourhoods are shaped by the gravitational tug-of-war between matter-rich regions and the expanding universe. The presence of matter slows local expansion. Gravity pulls structures together. Gas cools and condenses. Voids do not experience the same degree of opposing forces. Their lower density allows them to expand more quickly, creating wider gaps between the galaxies inside. Over time, these differences in expansion accentuate the contrast between filled regions and empty ones. It's not only matter density that differs. The temperature of the gas in these environments varies widely. In clusters, gas can reach millions of degrees, heated by gravitational compression and repeated interactions. In filaments, gas may still be warm, ionized by the ultraviolet background radiation permeating the universe. However, in voids, gas cools more easily. The lack of gravitational compression and the absence of large structures mean that gas can remain diffuse and cool. This too affects how galaxies inside these regions form and evolve. In denser regions, galaxies often lose their gas due to interactions with the cluster environment. This process, known as ram pressure stripping, removes the raw material needed to form new stars. In voids, this does not happen. A void galaxy can retain its gas for longer periods, slowly converting it into stars without major disruption. This difference in gas retention is one reason void galaxies sometimes appear bluer and more gas-rich than galaxies in clusters. Their star formation can proceed at a gentler pace. Another feature of ordinary cosmic neighbourhoods is the presence of gravitational interactions. In dense regions, galaxies may warp or distort each other's shapes through tidal forces. They can pull material from each other's outer layers, or even collide directly. These interactions are rare in voids. A galaxy in a void may go billions of years without encountering a significant gravitational disturbance from a neighbour. Its evolution becomes more dependent on its internal processes rather than external influences. This contrast reinforces how unusual the giant void is. In ordinary neighbourhoods, structure builds actively. Matter flows inward. Gravity shapes the distribution of galaxies. Inside a void, the opposite occurs. Matter flows outward. Gravity from surrounding structures pulls matter away. The internal evolution of the void is defined by absence rather than abundance. The presence of dark matter also highlights the difference between ordinary regions and voids. In dense areas, dark matter halos overlap and merge, creating massive gravitational wells. In voids, dark matter is present but stretched thin. Its distribution is smoother, its gravitational influence weaker. Because dark matter forms the framework on which galaxies build, this difference affects how galaxies inside voids come together. Fewer mergers occur, fewer satellites accompany larger galaxies. The result is a calmer, slower type of galactic history. Ordinary regions demonstrate the energetic side of the universe. Clusters radiate X-rays. Filaments glow in certain wavelengths. Star formation bursts occur where gas cools rapidly. In voids, the signals are quieter. The faint galaxies inside emit light, but they are rare. The gas, being thin, emits little radiation. From an observational standpoint, voids appear as darker patches with isolated points of light. This observational quietness does not mean that voids are dull. They hold clues to the universe's behaviour on the larger scales. Because voids have fewer gravitational complications, they can serve as clean test areas for models of cosmic expansion. Light passing through a void is less distorted by gravitational lensing. The expansion rate inside a void may differ slightly from the global average. These differences allow cosmologists to test theories about dark energy and gravitational physics. To see why ordinary neighbourhoods matter so much in comparison, consider that most of what we know about galaxy formation comes from observing galaxies in these environments. We see spirals forming in moderate density regions where gas inflow supports new stars. We see ellipticals forming in clusters where mergers dominate. We see starburst regions triggered by interactions. If voids were all we had to study, the picture would look very different. The diversity of galactic forms and behaviours arises from the wide range of environments the universe provides. Voids stand apart because they represent the extreme end of this spectrum. They are the places where gravitational influence is minimised, where the large-scale flow of matter points outward, and where the cosmic web thins to its faintest threads. But they also stand apart because they remind us that emptiness is not merely a lack, it is a consequence of structure elsewhere. A void is defined not by being separate from the cosmic web, but by being an integral part of it, shaped by the same forces that create clusters and filaments. Another way to understand the contrast is to look at how structure forms at different times in the universe's history. Early in cosmic evolution, matter was more evenly distributed. Over time, differences grew. Dense areas became denser. Sparse areas became sparser. This process continues today. Ordinary cosmic neighbourhoods are still evolving, with matter flowing along filaments and collecting in clusters. Voids are also evolving, expanding as matter continues to move outward. The giant void, therefore, is not a relic but an active part of ongoing cosmic development. When astronomers compare maps of the universe at different redshifts, they can track how these structures grow. Voids become more defined. Filaments stretch. Clusters increase in mass. These comparisons highlight the dynamic nature of the cosmos. The giant void stands out in such comparisons because its size suggests an unusually strong underdensity early in the universe's history. Its evolution may have diverged from more typical voids, leading to the extreme emptiness seen today. What lives in ordinary cosmic neighbourhoods are the building blocks of the luminous universe. Galaxies, clusters, filaments, and gas flows all interplay to create the rich structure we observe. These environments support the kind of galactic evolution that dominates most of the observable cosmos. Voids, by contrast, offer a quieter, more isolated environment where galaxies evolve with minimal interference. The contrast between these two environments clarifies why voids stand apart and why the giant void is even more striking. The giant void sits in a region of space that does not immediately announce itself. If you look toward it with an ordinary telescope, nothing dramatic would stand out. There are no bright signatures, no striking shapes, no unusual patterns marking its boundaries. What makes the region distinctive is not what is present, but what is missing. The familiar scaffolding of the cosmic web thins out so much that the ordinary texture of the universe fades into a quieter pattern. To astronomers accustomed to seeing the cosmos as a network filled with filaments, clusters and walls, this widening emptiness looks like a gap in the usual structure, a place where the web has loosened its threads far more than expected. When the giant void was first recognised, it was not its visual appearance that caught attention, but the statistical drop in galaxy density. This region displayed fewer galaxies than models predicted, and the emptiness extended over such an enormous range that simple explanations did not fit. At first glance, the number of galaxies seemed to fall off naturally, as though it were simply a slightly underdense patch in an otherwise ordinary map. But the emptiness continued. The region stretched outward in multiple directions, revealing volume after volume where galaxies were sparse. The further astronomers probed, the more striking the decline became. This pattern was unusual enough to suggest something beyond a random dip in density. The giant void's immensity was the next surprising feature. As the surveys expanded, the dimensions grew clearer. The void spanned a distance so long that comparing it to galaxy clusters or filaments scarcely captured its scale. A cluster, even a large one, is only a tiny structure in comparison. A filament, which might appear long on a map, is still a narrow strand relative to the vast open space in the void. The giant void encompasses a region so large that entire superclusters could fit inside it with ample room remaining. Because it is underdense, the light from the few galaxies within it must travel considerable distances before encountering another galaxy. This separation makes the region appear even emptier in three-dimensional maps. These maps reveal the void not as an absolute emptiness, but as a collection of thinner threads and isolated points. A few galaxies do exist, drifting quietly without significant gravitational neighbours. Some may sit at the edges of smaller, faint filaments that weave through the broader emptiness. But overall, the density of matter remains low enough that these features barely affect the void's character. The emptiness dominates. The galaxies present do not disrupt the impression of an expanse beyond familiar darkness, a region where the typical visual markers of large-scale structure nearly disappear. One of the reasons this region stands out so strongly is that it challenges our expectations about the distribution of matter. The cosmic web forms due to initial differences in density from the early universe. Denser regions attract matter more strongly, while less dense ones lose matter to their surroundings. Over time, these differences magnify. Voids become emptier, clusters grow denser. Most voids follow predictable patterns as this process continues. But the giant void appears more extreme. Its initial underdensity must have been greater than average for it to grow this large. It may represent a rare fluctuation from the early universe, a place where the initial conditions favoured rapid expansion and prolonged thinning. The environment inside the void is shaped by that history. Because the region contains so little matter, it offers few gravitational obstacles. The background expansion of the universe dominates. Space stretches slightly faster in underdense regions, causing the void to expand more rapidly than its surroundings. This process widens the void further, pushing galaxies apart and thinning the distribution of gas. Over billions of years, a self-reinforcing cycle develops. The void grows emptier, and its emptiness accelerates its expansion relative to denser areas. Galaxies within this region live in an unusual setting. Their isolation affects how they evolve. In denser areas, galaxies interact frequently. Encounters, mergers, and gravitational influences all change a galaxy's structure. In the giant void, interactions are rare. A galaxy may spend billions of years without experiencing a strong gravitational encounter. It evolves according to its internal processes, its shape determined more by the behaviour of its own dark matter, halo, and gas content than by external pressures. In some ways, galaxies in such an environment are like islands in an unbroken sea, shaped mostly by their own internal tides rather than currents carried from elsewhere. Observations of void galaxies often reveal interesting traits. Some appear less massive. Others contain more gas relative to their stellar content. Some have maintained their spiral structure longer than similar galaxies in crowded regions. Without nearby galaxies stripping away gas or distorting their shapes, they may retain features that are harder to preserve under more active conditions. The giant void's galaxies likely share some of these characteristics, though the exact details remain challenging to measure because the region is so distant and so faint. Still, the few galaxies within the void help define its presence. Their scarcity shows how unusual the environment is. Their positions provide clues to the boundaries and shape of the void, and their existence confirms that even the largest underdense regions are not completely empty. They contain the faintest traces of the cosmic web, thin remnants of a structure that, in other areas, forms elaborate patterns. The vastness of the giant void also affects light passing through it. A photon travelling across this region encounters less gravitational influence than it would in a denser part of the universe. This changes its path and energy slightly, contributing to subtle effects in observations. Some of these effects relate to the integrated Sachs-Wolf process, in which photons from the cosmic microwave background gain or lose energy as they pass through varying gravitational potentials. A void of sufficient size can influence this process, altering the temperature pattern seen in certain directions. While the giant void alone may not fully explain the microwave background anomalies observed in its vicinity, its size and underdensity make it a possible contributing factor. What makes the void intriguing is not just its size, but its potential role in broader cosmological questions. The universe's large-scale structure is shaped by dark matter, dark energy, and the expansion history of space itself. A void of unusual scale may help test certain theories. If its existence fits comfortably within predictions, it confirms that the early universe could produce such extreme underdensities. If it stretches beyond expectations, it might indicate that something in the models needs adjustment, perhaps the amount of dark matter, the properties of dark energy, or the initial spectrum of density fluctuations. Because the giant void stands at the far end of the distribution of void sizes, it occupies an important position in these discussions. It is not simply a curiosity. It is a boundary point in the landscape of cosmic structure. Its characteristics help define what is possible within the current understanding of cosmology. It pushes the limits of what gravitational evolution can produce. Examining the void's surroundings also reveals important patterns. The region does not exist in isolation. Its edges blend gradually into filaments and walls of galaxies. These boundaries are not sharp but transitional, where the density increases slowly. Near the edges, galaxies become more common, forming the faint strands that connect to denser regions farther away. These boundary regions show how the void fits within the larger cosmic web. Matter flows outward from the centre and collects at the edges, creating the structures that mark the void's borders. The shape of the giant void is also noteworthy. Voids are rarely perfect spheres. Their contours reflect the distribution of matter around them, creating irregular shapes that appear stretched or flattened depending on how gas and dark matter have moved. The giant void likely follows this irregular pattern, though determining its exact shape is difficult. Mapping such a large region requires combining data from multiple surveys, each with different depths and sensitivities. As new surveys expand their reach, the picture becomes clearer, but uncertainties remain. Despite these uncertainties, the void's presence is unmistakable. Multiple independent observations confirm its underdense nature. Galaxy surveys show the drop in numbers. Redshift measurements reveal the large-scale distribution. Infrared data helps fill gaps where dust might obscure galaxies. Radio observations detect gas in some parts of the region. Together, these datasets form a consistent picture of a massive, quiet expanse. The giant void also influences the motion of galaxies outside it. Regions with more matter exert gravitational pull, causing galaxies to move toward them. Voids, lacking matter, exert less pull. This difference affects how galaxies drift along the cosmic web. Around the boundary of a void, galaxies often show patterns of motion influenced by both the surrounding filaments and the emptiness behind them. These motions help refine models of the void's gravitational profile. Looking into such a region invites questions about what it means for the universe to have places like this. The presence of the giant void shows that the universe is not uniformly filled with structure. It has extremes, both dense and sparse. These extremes help balance the overall distribution and shape the large-scale behaviour of space. Without voids, the cosmic web would not form in the same way. Without dense regions, voids would not expand as they do. Both sides of this contrast are essential to understanding the universe as a whole. For listeners imagining the void, it may help to picture an immense landscape in which the familiar features gradually fade. In ordinary cosmic regions, clusters and filaments appear regularly. But in the giant void, those features recede until only faint traces remain. A few galaxies still shine, but they are spread across distances so large that they lose the sense of belonging to a structure. The void is not an absence in the everyday sense. It is a quiet amplification of the universe's natural tendency to separate matter into patterns of fullness and thinness. The silence of the void is not literal, of course. Sound does not travel in space. But the calmness of its structure, the lack of interactions, the slow evolution of galaxies, the gentle outward flow of matter, creates an environment that contrasts sharply with the active dynamism of clusters. It offers a glimpse into a part of the universe that evolves at a different pace, shaped by long stretches of time rather than quick changes. The boundary regions around a vast underdensity tell an important part of the story. While the interior of the giant void contains only faint traces of structure, its edges are where the cosmic web begins to reassemble itself. These areas show how matter responds to the gravitational landscape created by such a large empty space. The transition is gradual, not abrupt. Galaxies do not suddenly appear in a sharp line. Instead, their numbers increase slowly as one moves outward, following the influence of dark matter that has collected along the perimeter. These galaxies, sitting near the boundary, provide crucial information about how the void formed, how it continues to evolve, and how it interacts with the surrounding universe. The cosmic web is shaped by the flow of matter over billions of years. Gas and dark matter move along gravitational gradients toward denser regions, forming filaments and clusters. Voids expand as this process continues. The edges of a void therefore become natural gathering points where matter accumulates after flowing outward. These gathering points form the faint filaments and walls that mark the boundary. Galaxies in these locations, although still less numerous than in dense clusters, are far more common than those within the interior. Their properties reflect the unique conditions created by being close to a vast underdense region. These boundary galaxies often show signs of being part of long, thin structures that extend across great distances. Filaments are not uniform tubes. They vary in thickness, density, and length. Some are robust, filled with many galaxies and gas clouds. Others are delicate, containing just enough material to reveal the path of dark matter beneath them. In the parts surrounding the giant void, many of the filaments fall into this thinner category. They form a web-like outline around the empty centre, providing the first hints of structure after the immense quietness inside. Astronomers study these edge galaxies carefully because they serve as markers. Their distribution reveals the shape of the void's boundary. Their motions reveal how matter is flowing. Galaxies near the boundary often drift outward from the void and inward toward denser areas simultaneously. Their velocities reflect a balance between the pull of clusters far away and the expansion occurring inside the void. By measuring these motions, researchers gain insight into the gravitational environment of the region. Even subtle differences in velocity can indicate how mass is distributed just beyond what telescopes can see directly. The way light travels through these edges also provides useful information. When light from distant galaxies passes near the boundary of a void, the gravitational field can alter the path slightly. This effect, known as weak gravitational lensing, can reveal how much dark matter is present in these edge filaments. By mapping the distortions, scientists can reconstruct the structure of the surrounding web. For a void as large as the giant void, this lensing effect stretches across a wide region of the sky. The cumulative signal, though still subtle, becomes easier to measure as more data is collected. Understanding these boundary structures also helps refine models of how the cosmic web forms. The distribution of void sizes depends partly on how filaments grow. In places where filaments are robust, voids tend to be smaller. In places where filaments are thin or interrupted, voids can expand more freely. The giant void suggests that the surrounding filaments are weaker than those found around typical voids. The reasons for this weakness may lie in the early density variations that shape the region. If the initial fluctuations were lower in amplitude here, the resulting filaments would contain less mass, making it easier for the void to widen. The galaxies on the edge also show interesting evolutionary patterns. Because they sit near a boundary, they experience a mix of influences. They are not as isolated as the galaxies inside the void, nor are they as tightly bound by gravitational forces as those in clusters. Their interactions are moderate. They may encounter a few neighbours over billions of years, but seldom in the dramatic fashion seen in denser regions. This environment can produce galaxies with intermediate characteristics. Some may retain spiral forms with fewer distortions, while others may begin transitioning toward elliptical shapes at a slower pace. The gas content of these edge galaxies is another important clue. Gas availability influences how many stars a galaxy can form. In clusters, galaxies often lose gas due to interactions with the hot, dense environments. Near a void boundary, this stripping is less intense. As a result, some galaxies at the edge may retain more gas, allowing them to sustain star formation longer than similar galaxies in denser areas. Comparing their gas content with galaxies farther away helps scientists understand how environment shapes long-term evolution. The boundary region also contains clues about how matter flows through the cosmic web. Within filaments, gas and dark matter move gradually toward nodes where clusters form. Near a void boundary, this flow often bends around the empty region, following paths shaped by the gravitational pull of dense structures outside the void. These flow patterns reveal how the void interacts with the rest of the universe. They show the gradual transition from the calm interior to the dynamic outer regions where matter gathers. To map these flows, astronomers use redshift surveys that measure the velocities of galaxies along the line of sight. By comparing redshifts with expected distances, they can determine how fast galaxies are moving and in which direction. These data show that galaxies near a void's boundary often have slightly higher peculiar velocities, meaning their movements deviate from the general expansion of the universe. These deviations are caused by gravitational gradients at the edges, where matter density increases. For the giant void, these gradients are spread across a very large region, affecting galaxies over hundreds of millions of light years. The structure of the cosmic web around the void also reveals how matter was initially distributed. By examining the thickness and connectivity of filaments, researchers can infer the early conditions that led to the formation of such an extreme underdensity. If the filament network appears unusually thin or sparse, it may indicate that the initial environment lacked the small fluctuations that seed dense structures. These differences can be compared with simulations to refine models of how the cosmic web grows from early conditions. What makes the giant void's boundary especially interesting is how it highlights the contrast between emptiness and structure. On one side lies a vast region where galaxies are rare, and the gravitational field is unusually smooth. On the other side, filaments and walls stretch outward, forming part of the familiar cosmic landscape. This contrast helps define the void's identity. It is not the absence of the web, but a reshaping of it, a place where the usual patterns are stretched thin by billions of years of divergent gravitational forces. One might imagine these edge galaxies as forming the outline of an enormous cavity carved into the universe. But the reality is more subtle. Voids expand because matter flows away from underdense regions, not because something hollowed them out. The boundary galaxies are simply the leftover structures that did not move outward fast enough to remain within the expanding emptiness. They represent the points where the cosmic web resisted the expansion, gathering material that no longer remained in the void. Because the giant void covers such a large volume, its boundary includes many of these faint filaments. Each filament serves as a reminder of how the void fits within the larger cosmic network. Some filaments may connect to clusters far outside the region. Others may branch into smaller structures. Together, they form a pattern that helps reconstruct the void's shape and history. The galaxies near the boundary can also show signs of the gravitational influence of the void itself. A galaxy moving near the edge may feel a slight outward tug from the lower density interior, and a stronger inward pull from a denser region beyond. These competing forces shape its trajectory. Over long timescales, the galaxy's position may shift as it follows the combined gravitational guidance of nearby structures. Mapping these trajectories provides additional information about the void's gravitational profile. Despite the relative thinness of the cosmic web here, these edge filaments still contain multiple types of galaxies. Some are small, faint and irregular. Others are larger spirals or ellipticals. Their diversity reflects the varied conditions of the early universe and the long-term effects of their environments. By studying which types of galaxies appear at the edge and how they are distributed, astronomers can determine whether certain conditions favour the formation of particular galaxy types. These patterns also reveal how the void influenced the growth of nearby structures. The edge of the void is not static. As the universe expands, the boundary shifts outward. Galaxies that once sat well within the void may now lie near its edge, or even outside it as the void grows. This does not happen quickly. Billions of years pass before significant changes accumulate. But the process demonstrates the dynamic nature of voids. They are not fixed cavities, but evolving structures that respond to the ongoing expansion of the universe. This dynamic behaviour contributes to the uniqueness of the giant void. Its size and continued expansion affect the large-scale flow of matter and the shape of surrounding structures. The boundary region reflects these influences through variations in galaxy density, motion, and distribution. Each piece of data helps refine the understanding of how such a large emptiness can exist and how it fits into cosmological models. The galaxies on the edge serve not only as markers, but as tools. They allow scientists to probe the void indirectly. By studying them, researchers can estimate how dark matter is distributed, how the void has evolved, and how gravity shapes the cosmic web on the larger scales. The giant void, despite its emptiness, influences everything around it. Its edges are the places where this influence becomes visible. These boundary regions also provide a bridge between the emptiness inside and the dense structures outside. They show how the cosmic web transitions from one extreme to another. Without this transition, the universe would appear more fragmented. Instead, the gradual increase in density from the void's interior to its boundary to the filaments beyond reveals the continuous nature of cosmic structure. The presence of emptiness in the universe is not an accident. It is a natural outcome of the same physics that forms galaxies, clusters, and filaments. In the earliest moments after the Big Bang, matter was distributed almost uniformly, with only slight variations in density. These variations were incredibly small, but over billions of years gravity magnified them. Regions with slightly more matter attracted additional material, becoming denser. Regions with slightly less matter lost material to their surroundings, becoming thinner. This process created the large-scale structure of the universe. Dense regions grew into clusters, medium regions became filaments and walls, underdense regions expanded into voids. The physics behind this behaviour is well understood. Gravity draws matter into some places and away from others. Once a region becomes underdense enough, its evolution begins to diverge from that of its surroundings. Because of this gravitational sorting, emptiness is not unexpected. In fact, more than half of the volume of the observable universe is contained within voids of various sizes. Most of these voids are relatively small on cosmic scales, perhaps tens of millions of light-years across. Their presence fits neatly into models of cosmic evolution. Computer simulations designed to replicate the growth of structure consistently produce voids, filaments, and clusters in patterns that closely resemble what telescopes reveal. The existence of emptiness is therefore not surprising. What matters are the details, the sizes of voids, the shapes they form, the smoothness of their interiors, and the behaviour of the matter within them. When physicists model the early universe, they begin with the fluctuations imprinted during cosmic inflation. Inflation stretched space so rapidly that quantum variations in density were magnified to astronomical scales. These variations provided the seeds for all later structure, The distribution of these initial fluctuations determines how many dense areas, moderate areas, and sparse areas will form. Most fluctuations fall into a predictable range. Some regions start slightly denser, some slightly thinner, but the differences are small. Over time, gravity exaggerates these initial seeds, forming the cosmic web. Voids emerge from the regions that started just a little below average density. Under typical conditions, these voids grow as the universe expands. Their lower density means they exert less gravitational pull. While matter is drawn toward denser regions, the voids effectively lose matter. This dynamic creates an outward flow, a gentle migration of material away from the interior toward the surrounding filaments. As matter leaves, the void grows larger. This process continues indefinitely, provided the region remains underdense. The expansion of the universe amplifies this behavior further, because space itself stretches. The void interior expands more quickly than denser areas, widening the chasm between structures. All of this is expected. It follows directly from how gravity and cosmic expansion behave. Yet the giant void still raises questions because it appears to be more extreme than most models predict. The physics explains why voids form. It explains why they grow. It explains why their interiors are smooth and their boundaries shaped by the surrounding web. But the sheer scale of the giant void challenges assumptions about how large such regions can become under typical conditions. One of the first surprises is the void's volume. Given the usual distribution of initial density fluctuations, extremely large voids should be rare. Simulations show a broad range of void sizes, but the largest ones generally fall below the size of the giant void. A void of this scale requires an initial underdensity more extreme than what occurs in most realizations of the early universe. While such extreme fluctuations are not impossible, they are statistically uncommon. If the giant void resulted from one of these rare initial conditions, it suggests that the early universe produced at least some unusual deviations from the average pattern. Another surprise comes from the void's smoothness. Many voids contain small substructures formed from the remnants of faint filaments or groups of galaxies that never fully evacuated the region. These substructures disrupt the smoothness of the underdensity. The giant void, however, appears exceptionally smooth. It is not perfectly empty, but the lack of noticeable internal filaments or smaller voids suggests that the region's evolution followed a particularly clean path. The contrast between its smooth interior and the thin boundary filaments stands out. This smoothness may indicate that the void did not experience the same level of internal mergers or interactions that shaped other parts of the cosmic web. The void's location also contributes to its intrigue. It lies in a part of the sky where the microwave background shows an unusual feature known as the cold spot. This region of the cosmic microwave background appears slightly cooler than expected. Some researchers have proposed a connection between the two, suggesting that the void may influence the temperature pattern through gravitational effects. When photons from the cosmic microwave background pass through a large underdense region, they experience changes in energy due to the integrated Sachs-Wolf effect. This effect is subtle, but a void as large as the giant void could contribute to the observed temperature difference. However, whether it can fully account for the cold spot remains debated. This uncertainty adds another layer of interest to the void, raising questions about whether it is a typical feature or part of a larger cosmological puzzle. The physics behind voids predicts that they should influence the motion of galaxies nearby. Galaxies at the boundary of a void feel less gravitational pull from the interior, causing them to drift outward toward denser regions. This outward motion creates a kind of bubble-like flow pattern. Measurements of galaxy velocities near the giant void suggest that such flow is occurring, but the magnitude of the effect must be matched carefully with predictions. If the flow is stronger or weaker than expected, it could imply that the void's density, shape, or dark matter distribution differs from current assumptions. Dark matter plays a central role in how voids evolve. It forms the invisible framework onto which visible matter attaches. The behaviour of dark matter determines how quickly a void expands and how sharply its boundaries develop. If the dark matter distribution in and around the giant void differs from what simulations predict, it could explain some of its unusual features. This raises questions about whether the void reflects normal dark matter behaviour, or whether it hints at subtle differences in how dark matter clumps at the larger scales. The role of dark energy also enters the discussion. Dark energy drives the accelerating expansion of the universe, affecting how voids grow over time. If dark energy behaves uniformly, voids should expand at predictable rates based on their density. But if dark energy has slight spatial variations, something some alternative theories explore, voids could expand differently in different regions. While no evidence currently supports such variations, large voids provide valuable testing grounds. Their expansion history offers a way to look for deviations from the expected behaviour of dark energy. If the giant void expands faster or slower than predicted, it might signal something subtle about the underlying physics. Even without invoking new physics, the giant void challenges cosmologists to refine their models of structure formation. The size distribution of voids depends sensitively on the statistical properties of the initial density fluctuations. If observations reveal more large voids than expected, it may suggest that the early universe had slightly different characteristics than currently assumed. These characteristics might include variations in the spectrum of initial fluctuations or differences in how matter and radiation interacted during early cosmic evolution. One area where the giant void continues to prompt questions is its relationship to other large-scale structures. In some maps, the void appears near other underdensities that form part of a broader pattern. Whether these features are related or merely coincidental remains uncertain. If they are related, the region might represent a complex network of interconnected voids rather than a single isolated structure. This possibility would change how astronomers interpret the void's formation. Large interconnected voids could arise from extended regions of the early universe that were underdense across many scales. If the giant void is part of such a network, its size might be more understandable within the framework of those initial conditions. The surprising nature of the void also stems from its low galaxy count. While voids are defined by low density, the giant void's galaxy population appears even lower than average for voids of similar size. Fewer galaxies mean fewer tracers for mapping the interior. This lack of tracers complicates efforts to determine the void's exact structure, but it also raises questions about why galaxy formation was so suppressed in the region. Several possibilities exist. The initial density may have been so low that few dark matter halos reached the mass threshold required to form galaxies. Alternatively, the region's early environment may have lacked the gas conditions needed for efficient star formation. Whatever the cause, the scarcity of galaxies contributes to the perception of extreme emptiness. Another reason the void stands out is that it seems to push the statistical boundaries of what is likely. Simulations produce voids of many sizes, including some that approach the scale of the giant void. But the frequency of such large voids is extremely low. Finding one in the observable universe is not impossible, but it lies near the tail of the distribution. The fact that we have detected one raises the question of whether it is simply a rare example, or whether our understanding of the distribution needs refinement. If even larger voids exist but remain undetected, the picture of cosmic structure may need adjustment. The void also surprises because it serves as an example of how the universe remains capable of producing extreme structures despite following well-understood physical laws. Gravity, expansion, and the initial conditions all work together to shape the cosmos. Yet within this framework, rare and unusual features still emerge. The giant void is one of those features. It is not beyond explanation, but it challenges the boundaries of what is considered typical. This challenge becomes clearer when comparing the void with nearby structures. Dense regions follow predictable patterns as they grow through mergers and accretion. Voids should likewise follow patterns governed by the removal of matter and the expansion of space. If the giant void grew faster or reached a larger scale than models predict, it suggests that something in the region's history diverged from the usual path. That divergence may reflect unusual initial conditions, variations in the growth rate of surrounding filaments, or differences in dark matter distribution. Studying these possibilities requires more than counting galaxies. It involves mapping subtle gravitational effects, measuring motions across enormous distances, and comparing observations with high-resolution simulations. As technology improves, more voids will be mapped in greater detail. These comparisons will help clarify whether the giant void is an outlier or one example of a larger class of extreme underdensities. What makes the void particularly valuable is that it pushes researchers to test the limits of their theories. Voids are sensitive indicators of cosmic evolution. They respond differently to changes in dark energy, dark matter behaviour, and initial conditions than dense regions do. Because they are less complicated by interactions and mergers, their evolution is cleaner and easier to interpret. A void as large as the giant void therefore becomes a useful case study. If models can account for it accurately, confidence in those models grows. If discrepancies remain, the void may point the way toward refinements in our understanding of the universe. The few galaxies that inhabit the giant void present an unusual picture. They exist in a region where the cosmic web has thinned so dramatically that the usual connections between galaxies almost disappear. Their closest neighbours are often incredibly far away, sometimes tens or even hundreds of millions of light-years distant. This separation is not just spatial, it shapes the entire course of their evolution. The isolation inside such a large underdensity affects how these galaxies form stars, how their structures develop, and how they interact with the surrounding environment. The result is a population of objects that evolve under conditions unlike those found in most parts of the universe. When astronomers examine galaxies in typical environments, they expect to see various influences shaping them. Nearby galaxies may pull on each other gravitationally, triggering tidal distortions or encouraging the inflow of gas that sparks star formation. Groups and clusters can strip gas from galaxies, shutting down the processes needed to form stars. Filaments can channel fresh gas toward galaxies, supplying them with material for growth. Inside the giant void, many of these interactions are absent or extremely rare. A galaxy might go billions of years without experiencing any close encounter. This isolation means that its development is guided primarily by internal processes and the slow inflow of gas from its own small dark matter halo. Because galaxies in voids lack the disruptive forces found in clusters and dense filaments, they often retain features that might otherwise be altered. Spiral galaxies can maintain their disks for long periods. Even faint irregular galaxies may hold on to their gas longer than expected. Observations from smaller voids across the universe show that void galaxies tend to have higher gas fractions, younger stellar populations, and more active star formation relative to their mass. If these patterns hold in the giant void, the few galaxies inside it may be forming stars at a slow but steady pace, shaped not by external pressures but by the gentle cooling of gas in an environment free from major disturbances. The gas content of these galaxies is key to understanding their behaviour. In a typical galaxy, gas can be replenished or stripped depending on the environment. In clusters, galaxy interactions and the hot intracluster medium often remove gas rapidly. In filaments, inflowing gas can sustain star formation. Inside the giant void, the inflow of gas is weaker, but so are the stripping mechanisms. As a result, a galaxy may build a reservoir of gas and convert it slowly into stars. The star formation rate may be modest, but it can continue over long timescales. This leads to a population of galaxies that appear faint yet relatively blue, with ongoing star formation despite their isolation. The lack of nearby galaxies also affects the shape and structure of void galaxies. Without strong tidal forces, their disks may remain undisturbed. Bars, spiral arms, and other features may develop differently, or maintain their form for longer periods. In dense environments, galaxy mergers occur regularly. These mergers transform spirals into elliptical galaxies, change star formation rates, and reshape the galactic halo. In a void, mergers are rare. A galaxy might interact with a small satellite or accrete a few clumps of gas, but the dramatic collisions that define galaxy evolution elsewhere are largely absent. The evolutionary path becomes calmer, guided by slow internal processes rather than energetic external events. These isolated galaxies offer insight into how the earliest galaxies might have evolved before the cosmic web became fully established. In the early universe, density variations were small, and galaxies often grew in relative isolation. Studying void galaxies provides a glimpse into that type of environment, albeit at a much later stage in cosmic history. Their conditions resemble those of the early cosmos more closely than galaxies in the bustling regions of the modern universe. This makes them valuable laboratories for understanding fundamental processes such as how gas cools, how dark matter halos influence star formation, and how internal dynamics shape galaxy morphology. Another interesting aspect of these galaxies is their motion. Inside the void, the overall gravitational field is smoother than in denser areas. The uneven distribution of matter that characterizes clusters and filaments creates gravitational tugging that influences galaxy velocities. In a void, most of these tugging forces are absent. Galaxies drift slowly, influenced by the slight pull of nearby filaments at the boundary and the overall expansion of space. Their motion tends to follow the expansion more closely than in dense regions. Over long timescales, this gentle movement carries them farther from each other, contributing to the region's growing emptiness. This motion also reflects how voids interact with their surroundings. While matter flows outward from the interior, galaxies near the centre experience weaker gravitational competition. They are carried along with the expanding space, their distances increasing gradually. The isolation becomes more pronounced over time. If a galaxy within the void once had a slightly closer neighbour, billions of years of expansion may have widened the gap until interactions became virtually impossible. The result is a population of galaxies whose histories diverge from the standard evolutionary paths shaped by close encounters. Some galaxies inside the giant void may belong to small, faint groups. Even inside an underdense region, small pockets of matter can cluster together. These groups, however, are far sparser than comparable groups in typical environments. They may contain only a few galaxies or none large enough to be easily detected. The interactions within these small groups are minimal, but they can still influence galaxy evolution slightly. A faint satellite might merge with a larger galaxy over time, contributing a small amount of mass. These events are minor compared with the major mergers seen elsewhere, but they still shape the long-term history of the void's galaxies. The dark matter halos surrounding these galaxies also behave differently in the void environment. In denser regions, halos merge rapidly, forming the massive structures that anchor galaxy clusters. In voids, halo mergers are infrequent. A halo may remain relatively undisturbed, growing slowly through the accretion of small amounts of dark matter rather than through major mergers. This slow growth influences the availability of gas and the potential for star formation. The structure of the dark matter halo plays a significant role in shaping the galaxy's development. A stable halo can maintain a regular inflow of gas for long periods, supporting a slow and steady rate of star formation. Because void galaxies evolve in such calm conditions, they may appear younger in some respects than galaxies in more crowded environments. Their star formation histories differ because they experience fewer events that quench or boost their activity. As a result, some void galaxies retain significant amounts of cold gas even in the present-day universe. Their stellar populations may show a mix of older stars formed early in cosmic history and younger stars formed gradually over billions of years. This extended star formation can give void galaxies distinctive spectral properties compared to their counterparts in denser environments. The isolation also means that these galaxies provide a relatively clean signal when studied through telescopes. Without interference from nearby galaxies or complex background structures, their properties can be measured more clearly. The light from these galaxies travels through long stretches of low-density space, encountering fewer gravitational distortions. This allows astronomers to analyse their structure, composition and star formation rates with greater precision. Studying these galaxies becomes a way to test fundamental ideas about how galaxies behave when left largely to their own devices. Despite their isolation, the galaxies inside the giant void are not entirely disconnected from the rest of the universe. Over immense timescales, the expansion of the void brings them closer to the boundary regions where the cosmic web becomes more prominent. Gas and dark matter flows along faint filaments can still reach them, albeit in smaller quantities. These flows may shape their growth in subtle ways. A trickle of fresh gas entering a galaxy's halo can sustain star formation, even if the overall supply is limited. These slow, steady inflows reflect the delicate balance of the void's internal environment. Galaxies in the void may also provide hints about the early conditions that created such an extreme underdensity. Their distribution, composition, and motion can be traced back to initial fluctuations. If the void's galaxies share common traits that differ from typical galaxies, it may indicate that the region's initial conditions were distinctive. For example, if their dark matter halos show signs of forming earlier or later than halos in denser regions, it could provide clues about how the void developed through cosmic history. These details help refine models of how rare underdense regions evolve. One of the challenges in studying these galaxies is their faintness. Because they are isolated and often low in mass, their brightness is limited. Telescopes must gather light over long exposures to reveal their details. Some may be too faint to detect with current instruments. Others may be hidden behind regions of the sky where our galaxy's dust blocks the view. Even so, the galaxies that can be observed provide valuable information. They serve as anchor points for mapping the void's interior, tracing the subtle structures that remain despite the overall emptiness. It's possible that future surveys will uncover more galaxies inside the void, especially as instruments become more sensitive to faint, distant objects. Deeper infrared and radio observations could reveal galaxies missed by earlier optical surveys. Discovering more galaxies would help refine the void's profile and clarify how extreme the underdensity truly is. But even with more discoveries, the overall picture would remain the same. The giant void is sparsely populated, and its galaxies are separated by distances far greater than those in typical environments. This scarcity influences not only galactic evolution, but also cosmological measurements. Galaxies serve as tracers for mapping the universe's structure. When a region contains very few tracers, uncertainties increase. The interior of the giant void presents such uncertainties. Astronomers must piece together the void structure from limited data points, inferring the shape and density of the region from a small population of galaxies. This makes the void an intriguing challenge for observational cosmology, pushing the limits of current mapping techniques. Although the void's galaxies are few, they form an essential part of the story. Without them, the void would be invisible. Its presence would be harder to confirm. These lonely objects act as markers within an immense underdensity, revealing the location, extent, and character of the region. Their existence shows that even the largest empty spaces in the universe are not truly empty. They contain remnants of the cosmic web, quiet and sparse, but still connected to the broader structure. Their isolation also helps highlight the contrast between voids and typical environments. The differences in their evolution, gas content, star formation, and structure illuminate how environment shapes galaxies over time. They remind us that the universe is not uniform, and that galaxies are not defined solely by their internal properties. The places where they live matter, and in the case of the giant void, those places are nearly as empty as the universe can produce. The giant void does not stand alone in the structure of the universe. It is part of a larger tapestry made of enormous underdensities and towering overdensities that stretch across billions of light years. These structures are not random. They follow patterns shaped by the early conditions of the universe and the long history of gravity acting on matter. When astronomers step back far enough, the cosmos reveals an intricate layout of supervoids and superclusters, each influencing the behaviour of galaxies, dark matter, and the expansion of space. Understanding how the giant void fits into this larger architecture requires a careful look at how these major structures form, how they interact, and how they help define the landscape of the universe. The term supervoid refers to an underdense region far larger than the typical voids found throughout the cosmos. While many voids span tens or hundreds of millions of light years, supervoids can stretch for hundreds of millions to over 1 billion light years. The giant void meets that definition and extends it further. Its size places it at the extreme end of the distribution, making it one of the largest known. But it is not entirely alone in this category. Other supervoids have been identified, though most are smaller and less underdense than the giant void. These supervoids often appear connected to each other in subtle ways, forming parts of a larger pattern that reflects how matter moved in the early universe. On the opposite end of the density spectrum lie superstructures, which include superclusters, walls, and filaments. These are massive arrangements of galaxies held together by dark matter. They are not single objects in the same way a galaxy is an object. Rather, they are groupings of many clusters and filaments that align over enormous distances. The Virgo supercluster, which includes our own galaxy, is one example, though by cosmic standards it is modest in size. Even larger structures, such as the Sloan Great Wall or the Hercules Corona Borealis Great Wall, stretch across billions of light years. These immense features stand in contrast to the empty regions, creating sharp differences in density across the cosmic landscape. The relationship between supervoids and superstructures is essential for understanding the universe's large-scale design. They do not form in isolation. Their development is linked through gravitational interactions that occur over cosmic time. In the early universe, small variations in density caused matter to collect in some areas and dissipate from others. Over time, these variations grew larger. Dense regions became even denser, creating the seeds of future superclusters. Sparse regions became sparser, expanding into voids and eventually supervoids. The balance between these two extremes helped shape the cosmic web. When examining the cosmic web on the larger scales, the pattern that emerges is one of interconnected filaments surrounding vast voids. The filaments form the backbone of the visible universe. They guide the flow of gas and dark matter, channel galaxies toward clusters, and define the paths of gravitational influence. Between them, the voids stretch like open pockets, each with its own shape, size, and evolutionary path. Supervoids, including the giant void, represent the largest of these pockets. The distribution of these structures is not perfectly uniform. Some regions of the universe contain dense networks of filaments and numerous clusters, while others contain multiple voids grouped together. These void-rich regions can create large-scale patterns that span significant portions of the observable universe. The giant void may be part of one such pattern, although determining this with high precision requires extensive mapping. One interesting aspect of the universe's architecture is how superstructures and supervoids appear to balance each other statistically. If a region contains a large supercluster, nearby regions often contain larger voids. If clusters are smaller and less massive, voids may also be smaller. This balancing act reflects the way matter redistributes itself under gravity. For the giant void, its existence implies that surrounding structures may contain unusual densities or arrangements. Some data suggest that regions beyond the void's boundary include filaments that connect to distant superclusters. Whether these connections extend in predictable ways is still under investigation, but they demonstrate how the void fits into the broader cosmic network. The formation of superstructures involves processes that play out over billions of years. Dark matter halos merge and grow, pulling in gas that cools and forms galaxies. These galaxies, through their gravitational pull, affect the motion of others around them, shaping the overall flow of matter. The largest superclusters form at the intersections of multiple filaments, where the gravitational pull is strongest. These intersections serve as anchors in the cosmic web, drawing matter from vast distances. As these regions grow, the surrounding voids expand, creating a contrasting pattern where the universe becomes a network of dense knots surrounded by large expanses of thinning matter. Understanding supervoids requires recognizing that their formation is not simply the absence of dense structures, but the result of the same gravitational processes that create superclusters. If a region begins with slightly fewer density seeds during the early universe, gravitational forces will draw matter away from that region over billions of years. The emptying accelerates as the surrounding structures become denser. This imbalance deepens the void and shapes its boundaries. The giant void may represent a region that started with an exceptionally low-density seed, leading to its enormous size today. The variety of superstructures across the cosmos highlights the diversity of cosmic environments. Some superclusters appear elongated, stretched along filaments. Others cluster around massive central nodes. Walls, large sheet-like structures of galaxies, extend across hundreds of millions of light-years. These structures show how interconnected the cosmos is. Even though the distances are enormous, the gravitational threads between these structures influence how matter moves. Supervoids, too, come in many shapes. Some are nearly spherical, while others are elongated or irregular. Their shapes reflect the distribution of surrounding matter. If a void is bordered by dense filaments on one side and moderate density regions on another, its expansion may be uneven. The giant void likely follows such an irregular pattern. Mapping these shapes requires detailed surveys that track the positions and distances of galaxies across vast areas. As surveys improve, the shapes of voids and superstructures become more refined. The existence of superstructures influences the expansion of space in their vicinity. Dense regions slow expansion locally because their gravitational pull counters the stretch of space. Underdense regions expand slightly faster. This difference in expansion rates contributes to the growth of supervoids. Over billions of years, these differences become significant, helping extreme voids like the giant void reach sizes that may initially seem unlikely. The surrounding superstructures, by exerting strong gravitational influence, effectively push matter away from the void and toward themselves. This dynamic interplay reinforces the contrast between the two types of structures. Another important factor in understanding the universe's strange architecture is the role of dark matter. Although invisible, dark matter forms the foundation of all large-scale structure. It creates the gravitational scaffolding that guides the formation of galaxies and clusters. Where dark matter is dense, structures form easily. Where dark matter is thin, voids develop. Supervoids represent regions where dark matter density remains low across extremely large volumes. Superstructures represent the opposite. Because dark matter does not interact with light, its distribution must be inferred from gravitational effects, such as the movement of galaxies and subtle distortions of light. These measurements reveal that the arrangement of dark matter closely follows the cosmic web, with its intricate collection of filaments and voids. One of the most striking features of the cosmic web is its scale. The largest structures are so vast that even light travelling at 300,000 kilometers per second would take billions of years to cross them. The Hercules Corona Borealis Great Wall, for example, spans more than 10 billion light-years, making it one of the largest structures ever detected. Such enormous features raise questions about the homogeneity of the universe, a principle stating that on large enough scales matter should be distributed uniformly. These giant structures challenge the idea of uniformity, although current data still suggests that homogeneity holds when considering even larger scales. The giant void contributes to this discussion, because it represents one extreme of the density spectrum. Its presence helps scientists test whether the universe behaves according to predictions based on the cosmological principle. If voids this large are extremely rare, their discovery must be understood statistically. If they are more common than expected, models may need refinement. Some studies suggest that the universe contains more large voids than predicted, while others argue that selection effects or observational limitations may skew the results. In any case, the giant void remains a guidepost for evaluating these questions. The architecture of the universe also includes patterns that emerge from the arrangement of superstructures and voids. Some maps of the cosmic web reveal apparent alignments or recurring shapes. Whether these patterns represent meaningful structure or statistical noise remains under investigation. The universe is large enough that occasional alignments are expected by chance. Nevertheless, the possibility of deeper patterns has fueled many studies of cosmic structure. One aspect that becomes clear when studying these enormous features is that the universe evolves at different rates in different regions. Dense areas evolve rapidly, forming stars, merging galaxies, and generating energetic events. Sparse areas evolve more slowly, with fewer interactions and a quieter history. This dichotomy shapes the universe's overall character. Superstructures represent the active centres of cosmic evolution, while supervoids represent regions where time seems to move more gently, shaped by the gradual thinning of matter. The boundaries between these extremes are especially informative. They show how matter moves from one state to another, how gravitational fields interact, and how the cosmic web adjusts over time. The giant void's boundary, with its thin filaments and sparse galaxies, is one such transition zone. It demonstrates how the universe moves from emptiness to structure, revealing the gradient between two very different environments. When scientists model the universe, they strive to match these large-scale patterns. Simulations using billions of particles can reproduce filaments, clusters, and voids with remarkable accuracy. These simulations help reveal how superstructures and supervoids form, how they grow, and how they influence each other. They also offer predictions about how many extreme voids should exist. The giant void, being larger than most predicted voids, challenges these models slightly, but not enough to break them. Instead, it lies near the outer limits of what models allow, serving as a test case for refining the predictions. The unusual architecture of the universe raises natural questions about whether these patterns reflect deeper principles, or whether they are simply the outcome of random processes governed by simple laws. Current understanding suggests that the cosmic web emerges from a combination of initial density fluctuations, dark matter behavior, and cosmic expansion. No additional mechanisms appear necessary. However, ongoing research explores whether any anomalies hint at new physics. Supervoids and superstructures both play roles in these investigations because they represent the extremes of cosmic density. The enormous scale of the giant void invites careful consideration of how the unseen components of the universe influence regions where matter is sparse. Dark matter and dark energy shape the cosmos in ways that ordinary matter alone cannot explain. Their effects become most noticeable when looking at the larger structures, including clusters, filaments, and voids. Since the giant void occupies a vast volume where galaxies are rare and gas is thin, its development provides an unusual environment in which to examine how these unseen components behave. Understanding their influence helps clarify why the void is so large, how it continues to expand, and what its existence implies for cosmic evolution. Dark matter forms the framework on which visible structures grow. It does not interact with light, making it impossible to see directly, but its gravitational influence shapes everything from the formation of galaxies to the arrangement of the cosmic web. In regions where dark matter density is high, matter collects readily. In regions where dark matter density is low, matter tends to disperse. Because voids represent areas where dark matter is especially thin, they offer insight into how wide-reaching dark matter's influence can be. The giant void, being one of the largest underdense regions known, serves as a natural laboratory for studying the extremes of dark matter distribution. In typical environments, dark matter halos merge and grow over time. These mergers lead to the formation of large clusters and superclusters. The presence of these halos determines where gas can cool, where stars can form, and how galaxies evolve. Inside a void, however, dark matter halos are much smaller and more widely separated. The scarcity of dark matter suppresses the formation of massive halos, limiting the growth of large galaxies. Smaller halos can still form, but their evolution is slow. This contributes to the sparse galaxy population seen in the giant void. The region did not accumulate enough dark matter in the early universe to seed the structures found elsewhere. This absence of strong dark matter concentrations also affects the gravitational potential within the void. In denser regions, gravitational wells create complex patterns of motion, pulling matter inward and influencing how galaxies drift along filaments. Inside a void, the gravitational potential is smoother. There are fewer wells to affect motion. The overall gravitational field is dominated by the outward flow, driven by the region's underdensity. Because dark matter helps sculpt these gravitational landscapes, the giant void structure reveals how the distribution of dark matter creates areas of relative calm within the broader cosmic web. The role of dark energy adds another layer of complexity. Dark energy drives the accelerated expansion of the universe, influencing the motion of galaxies over enormous distances. Its effects are subtle on small scales but become dominant when examining vast voids. In regions where matter density is low, the influence of dark energy becomes more apparent. Dense regions, with their strong gravitational pull, counteract the expansion slightly. Under dense regions, lacking such gravitational competition, expand more rapidly. The giant void exemplifies this behaviour. Its interior stretches more quickly than regions filled with clusters and superclusters, increasing the separation between the few galaxies inside. This differential expansion contributes to the void's growth. Dark energy accelerates the expansion of the universe uniformly, but the impact differs depending on local density. In dense regions, gravity counteracts dark energy more effectively. In voids, gravity is weaker, allowing dark energy's influence to dominate. Over billions of years, this creates a widening disparity between dense and sparse regions. The giant void likely expanded faster than typical voids because its initial underdensity provided less gravitational resistance. This helps explain why the void reached such an extreme size. The interplay between dark matter and dark energy helps determine how supervoids evolve. Dark matter provides the gravitational scaffolding, while dark energy shapes the large-scale expansion. The balance between the two influences how quickly matter flows out of the void and how fast the void itself grows. If the giant void began with particularly low dark matter density, its expansion would have been enhanced by dark energy from an early stage. This could explain why it grew large enough to sit at the edge of what cosmological models predict. Some researchers explore whether subtle variations in dark energy could influence the development of such extreme voids. The standard model assumes that dark energy is uniform across space, exerting the same influence everywhere. If this assumption holds, then all voids should expand in a similar manner once differences in density are taken into account. But alternative theories suggest that dark energy might vary slightly over large distances. If so, voids could provide the best places to look for such variations. Because their interiors contain little matter, the effects of dark energy would be easier to detect. If the giant void expanded more quickly than models predict, it might hint at subtle differences in dark energy behaviour. However, current evidence does not strongly support this possibility, and most researchers attribute the void's development to known physical processes. Another way dark matter may influence the void involves how it shapes the surrounding filaments. The cosmic web forms because dark matter coalesces into a network of nodes and strands. In regions surrounding the giant void, the filaments appear thinner and less massive than those around typical voids. This might indicate that the initial distribution of dark matter near this region was weaker. If the surrounding filaments were less dense, they would exert less gravitational pull on matter near the edge of the void. This could have allowed the void to expand more freely, contributing to its extreme size. The structure of these filaments, therefore, offers clues about how dark matter shaped the void's boundaries. The idea that dark matter influences the formation of supervoids also connects to broader questions about the early universe. Dark matter did not interact with radiation in the same way ordinary matter did. While radiation smoothed out fluctuations in ordinary matter during the early phases of cosmic evolution, dark matter retained more of its original variations. These variations strongly affected how the cosmic web formed. If the region that became the giant void contained fewer dark matter fluctuations, its development would naturally lead to a large underdensity. This scenario suggests that the void's size reflects initial conditions rather than unexpected behaviour in dark matter itself. Dark matter's influence inside the void remains subtle but important. Even though dark matter is sparse, it still shapes the motion of the few galaxies present. The galaxies within the void reside in small halos, formed from local concentrations of dark matter. These halos determine how gas cools, how stars form, and how the galaxies evolve. Because dark matter halos grow more slowly in voids, galaxies inside the void tend to be less massive and more isolated. Their low mass and limited interactions reflect the smooth gravitational environment shaped by the diffuse dark matter distribution. Understanding the behaviour of dark matter inside voids also helps refine theories of how the cosmic web evolves. Simulations that vary dark matter properties, such as its mass, interaction strength or distribution, can reveal how sensitive void formation is to these parameters. The giant void, by pushing the limits of void size, offers an opportunity to test these theories. If dark matter behaved differently in this region, its signature might appear in the void shape, galaxy distribution, or expansion history. So far, observations remain consistent with standard dark matter theories, but the void continues to serve as a useful point of comparison. Dark energy's influence becomes more important as one looks at the void's long-term evolution. As the expansion of the universe accelerates, the separation between galaxies increases faster over time. Dense regions will remain gravitationally bound, but voids will grow even emptier. Over trillions of years, voids like the giant void will dominate the cosmic landscape. Galaxies inside them will drift farther apart until interactions become impossible. The local environment will become even smoother as matter becomes more evenly distributed within the underdensity. The influence of dark energy ensures that the difference between dense regions and voids becomes more pronounced as the universe ages. This future evolution highlights the link between voids and dark energy. The giant void provides a glimpse of how cosmic expansion shapes the universe on the larger scales. Its continued growth reflects the steady push of dark energy. Its smooth interior demonstrates how the accelerated expansion reduces the influence of small gravitational variations. The void offers a window into how the universe will look in the distant future, when the expansion will dilute matter even further. Some theories propose that studying voids could reveal subtle differences in dark energy behaviour across space. If dark energy were not perfectly uniform, voids would be the first places where the variations would become evident. Their low-density interiors amplify the effects of dark energy, making them sensitive to even small differences. The giant void, due to its size, becomes a prime candidate for such studies. By comparing the expansion rate within the void to that in denser regions, researchers can look for inconsistencies. Current observations, however, have not revealed strong evidence for non-uniform dark energy. The void appears to align with theoretical expectations, though uncertainties remain. Another aspect of dark energy's influence relates to how light travels through the void. Photons from distant galaxies or from the cosmic microwave background pass through regions where gravitational potentials are shallow. As they do, dark energy's influence on the expansion of space alters their path and energy slightly. These effects are small but measurable. The giant void, by spanning such a large volume, may contribute to subtle temperature differences in the cosmic microwave background. Although it cannot fully explain the cold spot on its own, it may be part of the overall influence shaping that feature. Studying this interaction between light and the void helps refine models of dark energy's effects on cosmic structures. The combination of dark matter and dark energy also influences how the void interacts with surrounding superstructures. The boundaries of the void form where the gravitational pull of filaments and clusters balances the outward flow from the underdense region. Dark matter helps shape these boundaries by determining the mass of the surrounding structures. Dark energy influences their growth by affecting how quickly the space around them expands. Together, these components help define the void's shape and evolution. The giant void likely grew through a complex interplay between these forces. Its interior expanded rapidly because of dark energy. Its boundaries formed where dark matter concentrations resisted that expansion. The balance between the two determined how the void stretched across billions of light years. This balance continues to evolve, shaping the void as the universe ages. Understanding how dark matter and dark energy shape voids provides insight into the universe's overall structure. These components define the large-scale behavior of space, guiding how galaxies move and how structures form. The giant void, through its size and emptiness, highlights the consequence of these forces acting over immense timescales. It shows how the universe's hidden components create regions of extreme calm in the midst of cosmic complexity. The unusual size of the giant void has encouraged many attempts to explain why such an extreme underdensity exists. Although most of its features fit within standard cosmology, its scale places it near the edge of what is considered likely. Whenever an object or region sits near the boundary of probability, scientists explore alternative ideas to make sense of it. Some of these explanations rely on rare but plausible variations within known physics. Others consider more speculative possibilities. The goal is not to assume something exotic must be true, but to examine every angle carefully. As more data arrives and models improve, these ideas shift in relevance and clarity. One of the earliest questions raised about the giant void involves whether it is truly a single, coherent structure, or whether it is composed of several smaller voids that overlap. When surveys map the universe, they rely on galaxy positions to infer density. If the galaxy population inside a region is low, it may appear as one large void, even if the underlying dark matter distribution contains multiple pockets. Some studies suggest that the giant void may include more than one underdensity connected by thin regions of matter. If true, the combined structure could appear larger than any one void. However, even this arrangement would be unusual in scale, suggesting a region of the universe where conditions favoured the development of multiple large underdensities close to each other. Another line of inquiry considers whether the void is connected to the cosmic microwave background feature known as the cold spot. The cold spot is a region in the microwave background that appears cooler than most of the surrounding sky. Some researchers have proposed that a large underdensity along the line of sight could contribute to this temperature difference. As photons pass through a void, the shallower gravitational potential changes their energy slightly. This effect is known as the integrated Sachs-Wolf effect. In principle, a void the size of the giant void could produce a small but noticeable contribution to the cold spot. However, most analyses conclude that it cannot fully account for the entire feature. This discrepancy leaves open the question of whether the alignment between the void and the cold spot is coincidental or meaningful. Coincidences in cosmology are not uncommon. The universe contains countless structures and patterns, and enormous data sets can produce apparent alignments simply by chance. But coincidences like this often become focal points for further investigation. If multiple lines of evidence suggest that a region behaves differently than expected, researchers look more carefully at whether the anomaly reflects deeper principles. The relationship between the giant void and the cold spot continues to generate interest, not because it breaks established physics, but because it provides an opportunity to test theories about how light interacts with large underdensities. Some theories explore whether the giant void reflects a statistical fluctuation from the early universe that happened to be unusually large. When the cosmic microwave background formed, small density variations existed throughout space. These variations served as the seeds for future structure. Most regions had fluctuations of typical size, but rare regions may have experienced larger deviations. If the area that eventually became the giant void began with a particularly low-density seed, the region's later evolution would naturally lead to an unusually large void. This explanation does not require new physics. It simply relies on the statistical nature of initial fluctuations. The challenge is determining how rare such an initial fluctuation would be. Some models suggest that while possible, it lies close to the tail end of the distribution. Another mystery concerns the void's shape. Many voids are roughly spherical, though distortions occur due to the distribution of surrounding matter. The giant void, however, may have an elongated or irregular shape that differs from what simple models predict. These irregularities may reflect the arrangement of nearby filaments or the influence of surrounding superstructures. If the void's shape is significantly distorted, it could indicate that the region experienced unequal expansion or gravitational influences that differ from standard assumptions. Understanding the shape requires high-resolution maps of galaxy positions, which continue to improve with each new survey. Speculative theories sometimes enter the discussion not because they are likely, but because they help frame the limits of standard explanations. One such possibility is that the void contains clues about variations in dark energy. If dark energy behaved differently in some regions, voids could expand at different rates. A faster expanding region would clear out matter more efficiently, creating a larger void. Although current evidence does not support spatial variations in dark energy, studying extreme structures helps constrain these possibilities. The giant void, being a standout example, becomes an important reference point for testing such ideas. Another area of speculation involves the nature of dark matter. If dark matter had properties that differ from the standard model, such as slight interactions with itself or radiation, the growth of large structures could change. Cold dark matter, the dominant model, predicts a particular pattern of void sizes and filament shapes. Variations in dark matter properties could produce more extreme voids. While observations generally support the cold dark matter model, the giant void size encourages careful consideration of whether any small deviations might exist. Simulations that incorporate alternative dark matter scenarios sometimes produce larger underdensities, but these models often conflict with other observations. Nonetheless, exploring these alternatives helps refine the boundaries of what remains possible. Some theories consider whether the void is connected to patterns in the distribution of matter on even larger scales. Certain surveys have identified large-scale alignments in the orientation of galaxies, spin directions, or filament directions. These patterns may reflect processes that occurred in the early universe. If the giant void aligns with one of these patterns, it could suggest that the region formed as part of a broader structural feature. These possibilities remain under investigation, and it is difficult to distinguish between genuine physical patterns and statistical coincidences. One historical mystery surrounding the giant void involves the early difficulty in detecting it. The void did not become widely known until surveys became dense enough to map galaxy distributions across large parts of the sky. Even then, confirming its size required careful analysis to separate actual underdensities from gaps in survey coverage. As techniques improved, the picture became clearer, revealing a vast region where galaxies were sparse. Yet the initial difficulty raises questions about what other large structures might remain undetected. If the giant void was so difficult to confirm, it is possible that even larger underdensities exist beyond current detection limits. This uncertainty underscores the importance of expanding surveys and improving mapping methods. Another question relates to whether the void affects the motion of objects outside its boundaries. Some studies indicate that voids can influence galaxy motions across hundreds of millions of light years. The absence of mass inside a void reduces gravitational resistance to expansion, which can create outward flows. If the giant void is large enough, its gravitational influence could affect the motion of galaxies in the surrounding filaments. Detecting this influence requires precise measurements of galaxy velocities. Some analyses suggest that the void contributes to motions observed in nearby regions. Whether these motions match predictions remains an active area of research. One more area of interest touches on whether the void might contain faint structures that have not yet been mapped. Galaxies inside the void are sparse but not non-existent. Extremely faint galaxies, small groups, or thin filaments might populate the interior in ways that remain difficult to observe. Some of these structures could be too faint for current surveys to detect. As telescopes become more sensitive, more galaxies may be discovered inside the void. These discoveries could refine estimates of its density and shape. A region initially thought to be nearly empty may contain more structure than previously assumed, though still far less than typical environments. Even if new galaxies are found, the void would remain extremely underdense. But identifying faint structures could help clarify how the void formed and how its evolution compares to predictions. For example, if faint filaments cross the void, they might reflect early remnants of the cosmic web that never fully developed. If no such structures exist, it may indicate that the void evolved in an unusually smooth manner. Another set of questions concerns whether the void formed independently or as a result of interactions between neighbouring underdensities. Some simulations show that voids can merge over time as the regions between them expand. If multiple voids grew toward each other, they could combine into a larger underdensity. The resulting structure might appear as a single void even though it formed from multiple components. This process may help explain the giant void's size. If it formed from the merging of several moderate-sized voids, its final dimensions would exceed typical expectations without requiring an extremely rare initial fluctuation. This merging scenario also helps explain why the void's boundary filaments appear thin. If the region experienced multiple merging events, the surrounding filaments might have stretched or fragmented over time. These processes could create a perimeter that appears less robust than those around isolated voids. Studying these filaments in detail helps determine whether the void formed through merging or through the steady expansion of a single underdense region. Some interpretations suggest that the void may represent a combination of both processes. It could have begun as an unusually underdense region that later merged with others. This hybrid scenario would place the void at the extreme end of natural formation processes, while still remaining compatible with standard cosmology. The challenge lies in distinguishing between these possibilities using available data. Even though these theories differ in details, they all aim to explain a structure that is large but not impossibly so. None require a fundamental revision of physics, though some open the door to exploring alternatives. The key point is that the giant void sits near the boundary of expected behaviour. Structures near such boundaries often attract more attention because they offer opportunities to refine models and test assumptions. The mysteries surrounding the void do not diminish the consistency of the overall cosmic picture. Instead, they highlight how complex the universe is at large scales. The cosmic web is shaped by simple rules, but those rules produce outcomes that vary widely. Extreme underdensities like the giant void are part of this variation. They help clarify how gravity, dark matter, and cosmic expansion interact across billions of years. The existence of a region as large and underdense as the giant void provides more than an example of unusual cosmic structure. It offers a way to think about how the universe evolves on timescales far beyond human history. Its immense scale makes it sensitive to long-term trends in gravitational behaviour, cosmic expansion, and the distribution of matter, By examining how such a void formed and how it continues to change, scientists gain insight into what the distant future of the cosmos may look like. Large voids reveal patterns that will grow more pronounced as billions or trillions of years pass, making them valuable indicators of the broader direction of cosmic evolution. The first clue the giant void provides involves how matter distributes itself as the universe expands. Most models show that as time progresses, dense regions become more isolated, while underdense regions widen. The cosmic web stretches and structures drift apart. This trend already shapes the universe today, but an extreme void demonstrates the long-term outcome of these processes. The giant void represents a place where expansion has already outpaced the ability of gravitational forces to maintain structure. It shows how wide the gaps between galaxies can become when density drops low enough. As expansion accelerates, the universe will see more regions moving toward this level of emptiness. Voids grow not because matter vanishes, but because mass flows toward denser areas. The same process that created the cosmic web continues as long as gravity acts on matter. Dense structures draw material from the surrounding regions, while voids lose it. The giant void demonstrates how far this process can go. Its size implies that mass loss from underdense regions can reach extraordinary scales when the initial conditions favour that path. This offers a preview of how the universe might look when expansion removes even more matter from low-density regions. Over time, underdensities similar to the giant void will dominate the cosmic landscape, separating galaxies even more effectively than today. The void also highlights the transition from a universe dominated by matter to one dominated by dark energy. During earlier periods of cosmic history, matter played a larger role in shaping the universe. Gravity slowed the expansion, allowed structures to form, and influenced how voids grew. As dark energy took over, expansion began to accelerate. This shift amplified the growth of voids by reducing the ability of matter to counteract expansion. The giant void serves as evidence of how this regime change affects large-scale structure. Its profile shows how regions with low density react strongly to dark energy, expanding faster than the universe overall. This acceleration will continue, making voids more prominent as time passes. Examining voids also helps clarify which structures will remain bound as expansion accelerates. Galaxies and clusters are held together by strong gravitational forces. These structures will persist even as the universe continues to expand. Galaxies inside large voids, however, are far more vulnerable to being carried away by expanding space. The giant void's isolated galaxies reveal how weak gravitational binding becomes in low-density environments. Their interactions grow rare, their influence on each other fades, and their future trajectories depend almost entirely on cosmic expansion. This suggests that vast portions of the universe will eventually consist of isolated galaxies drifting farther apart until they become unreachable to one another. This isolation connects to a broader picture of cosmic fate. As expansion continues, regions like the giant void may become typical rather than exceptional. More areas of the universe will stretch until galaxies inside them lose contact with the rest of the cosmic web. Over extremely long timescales, only the gravitationally bound regions, clusters or groups will remain coherent. Everything else will drift apart. The giant void offers a glimpse into this future environment, showing how matter behaves when gravitational interactions weaken and the influence of dark energy becomes dominant. The vast distances between galaxies in the void demonstrate the direction in which the universe is heading. Another lesson comes from the smoothness of the void's interior. In dense regions, mergers and interactions constantly reshape galaxies. Inside the giant void, disturbance is minimal. The few galaxies that remain drift slowly, guided mainly by the overall expansion. This lacks the complexity seen elsewhere. The future universe may resemble this environment more closely as time passes. As structure formation slows and interactions become rare, the dynamics of the universe will become calmer. The giant void's smooth interior reflects this long-term trend, showing how the universe might appear once active formation, and merging processes have largely ceased. The void also helps illustrate how the flow of matter changes over time. During earlier cosmic periods, matter moved toward dense regions, building clusters and superclusters. Today, that flow continues, but the rate of structure growth has slowed because dark energy counteracts gravitational attraction. The giant void's existence on such a large scale highlights how far matter can migrate when initial density variations are pronounced. As expansion accelerates, this migration will diminish. Dense regions will stop growing significantly, while voids will continue to grow due to expansion alone. Studying the giant void clarifies how this transition unfolds, revealing the interplay between gravitational attraction and the accelerating expansion driven by dark energy. The shape of the void also provides information about the long-term evolution of cosmic structure. If the void is significantly elongated, it suggests that different parts of the universe may expand at slightly different rates, depending on local conditions. Although dark energy is believed to be uniform, the distribution of matter can influence expansion locally. The void's shape reveals how these factors play out on enormous scales. By understanding how region-specific conditions shape expansion today, scientists gain better insight into how differences in density will shape the future universe, even if dark energy behaves uniformly. The motion of galaxies inside and around the void offers another perspective. Inside the void, galaxies drift with the expansion, their velocities showing how little they are influenced by local gravitational fields. Near the edges, galaxies move outward as the void grows. These motions reveal how the contrast between low-density and high-density regions drives long-term trends in cosmic dynamics. If expansion continues to accelerate, these differences will become more pronounced. The giant void provides an extreme case of this behavior, making it a useful example for predicting how expansion may separate cosmic structures even further. One of the most informative aspects of studying voids involves how they affect observations of distant light. When light travels through a void, it experiences different gravitational conditions than when it travels through dense regions. These differences influence the apparent brightness or temperature of distant sources. The giant void's size means that these effects may be more noticeable along its line of sight. Understanding these effects helps refine predictions about how light will behave in the far future, when voids become even larger and more numerous. As the universe ages, more lines of sight will pass through underdense regions, altering the observable characteristics of distant galaxies. Studying the giant void helps quantify these changes. Another factor involves how voids influence the distribution of dark matter. The cosmic web's long-term evolution depends largely on how dark matter continues to shape gravitational potential. Dense regions will remain bound, but dark matter in voids will become increasingly spread out. This gradual thinning will make voids more uniform. The giant void provides a look at how diffuse dark matter can become when an underdensity reaches an extreme size. Over time, similar distributions may become widespread as dark energy stretches the universe. This shift will change how dark matter interacts with galaxies, reducing its ability to pull structures together and further reinforcing the dominance of expansion. The future of galaxy evolution can also be inferred from regions like the giant void. In typical environments, galaxies continue forming stars as long as they have access to gas. Inside voids, where gas inflow is limited, galaxies eventually exhaust their available material. Over long timescales, star formation slows and eventually stops. The few galaxies inside the void may reflect this trend. As the universe expands and voids grow, gas exchange between galaxies and the environments around them will diminish. The wider universe will gradually move toward this state of low or non-existent star formation. The giant void offers a view of how this process plays out in an environment where isolation is extreme. The void also provides insight into how gravitationally bound structures will fade from view as expansion continues. In time, galaxies outside a gravitationally bound region will recede beyond the cosmic horizon. Their light will no longer reach observers inside clusters or groups. The giant void's vast distances already create scenarios where galaxies are isolated enough that they can barely influence one another. Over trillions of years, similar isolation will occur everywhere, except within the rare regions where gravity remains strong enough to resist expansion. The behaviour of galaxies inside the void shows how limited interactions become when distances grow extremely large. Studying the giant void also helps clarify how the observable universe will shrink in terms of accessible structures. As expansion accelerates, the horizon will contract relative to the size of the universe. Distant regions will move beyond reach, leaving observers with a decreasing portion of the cosmic web visible. The giant void highlights this process by showing how much of the universe can remain empty even within the current observable range. This emptiness illustrates how much of the future universe will lie beyond observational reach. By understanding the void's scale, scientists can better estimate how quickly the horizon will shrink relative to structures that remain locally bound. The void also informs predictions about the long-term thermal history of the universe. As galaxies drift apart and star formation ceases, the universe will cool further. The sparse environment of the giant void offers a glimpse into regions where heating from star formation is minimal. In such places, gas remains cold and quiet. Over long timescales, similar conditions will become more common as galaxies exhaust their fuel and stop producing new stars. The universe will become a collection of isolated systems surrounded by expanding space and relic structures. Studying the void helps illustrate this future by showing how matter behaves in regions where star formation is already minimal. Another important aspect involves how the large-scale structure of the universe stabilizes. Although expansion continues indefinitely, the arrangement of bound structures will eventually freeze. Clusters and groups will stop growing significantly as inflow from surrounding regions ceases. The existence of the giant void shows how sharply these boundaries can form. Its extreme underdensity provides a contrast to the dense areas that remain bound by gravity. This contrast helps researchers understand how the cosmic web will eventually settle into a stable configuration where bound structures persist, while unbound regions thin out. The void also helps clarify how the information available to future observers will differ from what is available now. As expansion continues, many galaxies will fade from view. The enormous distances inside voids provide a preview of how inaccessible many regions will become. The isolation observed today inside the giant void may represent a typical environment for future observers living inside gravitationally bound systems. Their entire observable universe could resemble the interior of a modern supervoid. This gives the void broader significance, as it helps illustrate what the long-term future may feel like for any intelligence that exists far into cosmic time. The transitions visible in the giant void, slow gas depletion, minimal gravitational interaction, dominance of expansion, match trends predicted for the universe's distant fate. These similarities make extreme voids useful benchmarks for testing long-term cosmological models. They show how the universe behaves when key processes become slow and gentle, governed mostly by expansion rather than gravitational collapse. The void's behaviour confirms predictions that the large-scale universe moves toward increasing separation and decreasing interaction. Studying a region that contains so little matter presents challenges that require careful planning, large data sets, and techniques built specifically for environments where normal signals are almost absent. Most astronomical methods rely on the presence of stars, gas, or dust to reveal the structure of the universe. Telescopes gather light, map positions, and measure properties that depend on matter being plentiful enough to observe. A region like the giant void defies that approach. Its defining characteristic is scarcity. and scarcity does not produce bright signals. The absence of luminous material forces researchers to use indirect methods, piecing together the void's shape and behaviour from the few galaxies that inhabit it, and from the subtle effects it produces on light and motion. Studying this region becomes a detailed exercise in inference, pattern recognition, and statistical analysis. The first step in identifying any void begins with large-scale surveys that map the universe's galaxy distribution. Telescopes measure the positions and redshifts of millions of galaxies, creating catalogues that show where matter gathers and where it thins out. These catalogues are used to construct three-dimensional maps that reveal filaments, clusters, walls, and empty regions. When a portion of the map appears sparsely populated, algorithms can determine whether that region qualifies as a void. For a structure as large as the giant void, the underdensity becomes noticeable even in early versions of these maps. However, defining its boundaries requires much more detailed information. A void is not simply an empty space, but an area where density falls below a specific threshold. Determining the threshold involves counting galaxies and comparing local densities to average values. Distance measurements play a central role in this process. Redshift surveys provide a way to estimate how far galaxies are from Earth based on the stretching of their light. Higher redshifts correspond to more distant galaxies. However, voids complicate these measurements because the few galaxies within them tend to have smaller peculiar velocities, motions not caused by cosmic expansion, but by local gravitational influences. This means their redshifts reflect expansion more cleanly, which can help, but it also means that mapping them requires precise corrections to account for the smooth gravitational environment. When mapping a void, researchers must distinguish between galaxies that are genuinely within the underdensity and those that lie slightly beyond its boundaries. Even small errors in distance can change interpretations of the void shape. Galaxy surveys also rely on brightness thresholds. Many large surveys detect galaxies down to specific magnitudes. If a void contains galaxies that are too faint or small, they may fall below the detection limit. This creates the risk of overestimating the emptiness. To mitigate this, surveys combine optical, infrared, and radio observations to catch different types of galaxies. Some void galaxies emit radio waves due to their gas content, even if they appear faint in visible light. Combining data from multiple wavelengths helps construct a more complete picture of the void's interior. The giant void remains underdense even with these additional data sources, confirming that its emptiness is not an artifact of limited sensitivity. Another tool used to study such regions involves examining the large-scale velocity fields of galaxies. Although voids contain few galaxies, the galaxies around their boundaries can reveal how matter flows in and out of the region. By analysing galaxy velocities relative to the expected expansion rate, researchers identify patterns that indicate whether galaxies are moving away from the void's centre. These motions help outline the void's boundaries more accurately than galaxy counts alone. The flow of galaxies also reveals information about the gravitational potential inside the void. A smoother gravitational environment leads to more uniform outward motion. Weak gravitational lensing provides another method for studying underdense regions. While strong lensing occurs when massive clusters dramatically bend light, weak lensing involves subtle distortions of background galaxies by variations in the gravitational field. Even a void can influence light by altering the path it takes through space. The effect is extremely subtle, but with large data sets, the distortions can be measured statistically. Mapping these distortions allows researchers to reconstruct the distribution of dark matter, revealing the underlying structure of the void. In the case of the giant void, weak lensing measurements help confirm that the region contains less dark matter than surrounding filaments. This information helps refine estimates of the void's density and expansion. Another technique involves studying how light from the cosmic microwave background interacts with the void. As photons from the microwave background pass through an underdense region, they experience small changes in energy due to the gravitational potential. This is known as the integrated Sachs-Wolf effect. Although the shift is small, it can be detected by comparing microwave background temperatures across different regions of the sky. If a void is large enough, it can leave a measurable imprint. The giant void's potential connection to the cold spot makes this technique particularly relevant. By analysing temperature patterns in the microwave background and comparing them with models of void-induced distortions, researchers gauge the void's size, depth, and potential influence. Because the giant void spans such a large area, studying it requires combining data from multiple sky surveys. No single survey covers enough galaxies or depth to fully characterise it. Large-scale projects such as the Sloan Digital Sky Survey, the 2-micron All-Sky Survey, and various radio and infrared surveys each contribute pieces of information. Combining these datasets involves careful calibration to ensure that measurements from different instruments align correctly. Researchers must account for differences in sky coverage, sensitivity, observational noise, and survey strategies. When these datasets are merged, the void structure becomes clearer. The combined maps show patterns of underdensity that persist across different methods, reinforcing confidence that the void is a real and extreme feature. Simulations play an essential role in interpreting void data. Computer models that simulate cosmic evolution allow researchers to compare observations with theoretical expectations. These simulations track billions of particles representing dark matter and gas over billions of years. They produce networks of filaments, clusters, and voids that resemble the cosmic web. By identifying voids of varying sizes within these simulations, researchers build statistical distributions of expected void sizes and shapes. When comparing the giant void with these distributions, its size stands out, but does not fall completely outside expectations. This helps frame the void as a rare but possible structure. Simulations also reveal how voids combine, expand, and shift over time, offering ways to interpret the void's history. To understand the shape and extent of the giant void more precisely, scientists use algorithms designed specifically to identify voids. These algorithms examine galaxy maps and detect areas where density falls below certain thresholds. Some methods treat voids as spherical or elliptical, while others allow complex shapes defined by the absence of galaxies. The watershed method, for example, identifies voids by tracing density minima and expanding regions outward until they meet boundaries defined by higher density. This method can produce detailed representations of irregular void shapes. Applying these algorithms to the giant void reveals a region that is not perfectly spherical, but extends unevenly across space, suggesting a complex interplay between early density fluctuations and surrounding structures. The challenge of studying something so empty also requires careful statistical analysis. When dealing with few data points, random variations can mimic patterns. Researchers must determine whether the observed underdensity is statistically significant or whether it could result from random fluctuations in galaxy positions. This involves comparing the observed void with thousands of simulated universes, each generated with slight variations in initial conditions. If the observed void is larger or emptier than most simulated voids, it becomes statistically significant. In the case of the giant void, its size exceeds most predictions but remains within the outer tail of the distribution. This statistical framing helps determine whether the void is truly exceptional or simply rare. Another important approach involves searching for galaxies that may be too faint to appear in optical surveys. Deep imaging with powerful telescopes can reveal faint dwarf galaxies that reside inside voids. Detecting these galaxies requires long exposure times and sensitive detectors. If such galaxies are found, they provide additional tracers for mapping the void's interior. In the case of the giant void, few faint galaxies have been identified, reinforcing the region's extreme underdensity. However, future surveys with more powerful instruments may uncover more objects, refining the void's profile. Radio observations contribute valuable information about gas in and around the void. Some galaxies inside voids contain significant amounts of neutral hydrogen, which emits radio waves at a specific frequency. By scanning regions of the sky at this frequency, telescopes can detect gas-rich galaxies even when they are faint in visible light. These observations provide insight into galaxy formation inside voids. If void galaxies contain more gas on average, it confirms that the environment allows them to retain material that might be stripped in denser areas. Observing neutral hydrogen also helps trace the distribution of gas around the void boundary, revealing how the void interacts with surrounding filaments. Infrared observations add another layer of data. Dust and older stars emit strongly in infrared wavelengths. Infrared surveys can identify galaxies that optical surveys miss, helping build a more complete map of the void's interior. These data help determine whether the void contains hidden structures or whether its emptiness holds across multiple observational methods. In the giant void, infrared observations confirm that few galaxies occupy the region, even when searching across the infrared spectrum. This reinforces the view that the void's emptiness is real rather than a product of limited detection capabilities. The study of voids also benefits from improved distance measurement techniques. Standard candles, such as Type Ia supernovae, provide accurate distance estimates that help refine the positions of galaxies relative to the void. Standard rulers, such as baryon acoustic oscillations, also help calibrate distance scales across the universe. When these methods are applied to galaxies near the void's boundaries, they provide more precise maps of how the void is shaped and how it influences nearby structures. Better distance measurements reveal whether galaxies are inside the void or merely projected along its line of sight. Another subtle technique involves analysing the temperature and polarisation of the cosmic microwave background in regions that overlap with the void. Variations in these properties can reveal interactions between photons and the gravitational potential of the void. Although the changes are small, advanced analysis methods can extract meaningful signals. These signals contribute to a more complete understanding of how the void's gravitational field shapes the universe's background radiation, offering insight into its depth and size. Studying something so empty ultimately relies on combining many tools. No single method provides a complete picture. Galaxy counts alone cannot define the void. Velocity measurements alone cannot reveal its shape. Gravitational lensing alone cannot map its dark matter distribution. But when combined, these methods paint a consistent portrait of a region where matter is exceptionally rare. The emptiness becomes measurable through its interaction with light, gravity, and cosmic expansion. As these tools advance, new possibilities emerge. Upcoming surveys will map the positions of billions of galaxies with unprecedented precision. Telescopes with larger mirrors and more sensitive detectors will reveal faint objects inside voids. Improved simulations will refine predictions of void behaviour. These advancements will help clarify the giant void's structure, its origin, and its role within the cosmic web. They will also improve the ability to study other extreme underdensities, revealing patterns that expand understanding of the universe's architecture. Stepping back from measurements, models, and calculations, it becomes possible to consider what it means to drift through a region like the giant void. After examining the surveys, the gravitational signals, and the distributions of galaxies and dark matter, the scale of the underdensity becomes easier to understand intellectually. Yet there is another way to approach it, by imagining the experience of moving through a place where the usual features of the universe fade into the distance. Even without assigning emotion or metaphor, the conditions inside such an environment bring a different perspective on scale, time, and the nature of structure. It is a space defined not by what fills it, but by how little remains. The first noticeable aspect of drifting through the void is the distance between objects. In most parts of the universe, galaxies form patterns that, although widely spaced, still show some regularity. Filaments connect clusters, and smaller groups fill the gaps. In a region like the giant void, these patterns change dramatically. The nearest galaxy might lie hundreds of millions of light-years away. The light from such a galaxy would be faint, spread over a long path through nearly unchanging space. Identifying it would require long observations and careful measurement. The vast intervals between galaxies define the environment in a way that no cluster or filament can match. Inside this underdensity, time takes on a different quality. The processes that shape galaxies in dense environments, mergers, tidal distortions, gas stripping, occur rarely or not at all. Stars form more slowly. Interactions between galaxies are almost non-existent. A galaxy inside the void evolves primarily according to its internal processes, moving steadily along a trajectory set by its own dynamics and the gentle influence of cosmic expansion. This lack of external disturbance gives these galaxies an extended period of relative stability. Their histories play out quietly, unmarked by the dramatic events that shape galaxies in busier environments. Observing the few galaxies inside the void reinforces how different their experience is. Many retain characteristics that would be altered in clusters. Their disks remain intact. Their gas stores are less disturbed. Their star formation may continue at a low but steady rate. These behaviours reflect not only the scarcity of nearby galaxies, but also the overall calmness of the gravitational environment. The surrounding space does not pull them strongly in any one direction. Instead, they drift outward with the expansion, maintaining their distance from one another over billions of years. The wide spacing also changes how motion is perceived. A galaxy inside the void does not exhibit the same complex motion seen in dense regions. Its path reflects the expansion of the universe more directly. There are fewer gravitational wells to alter its trajectory. The large-scale flow of matter that shapes filaments and clusters is weak here. Instead, the galaxy moves along a smoother and more predictable path. Its motion adds to the sense of drifting through a region where gravitational interactions are gentle, shaped more by the general expansion than by local forces. Light also behaves differently when it travels through such an open environment. In denser regions, light from distant objects may be slightly bent or magnified by foreground structures. Inside a large underdensity, these effects are minimal. Light travels long distances without encountering strong gravitational distortions. The path remains stable, influenced only by the gradual expansion of space. This makes the void a useful reference for measuring large-scale cosmic properties, because it imposes fewer local distortions. But from a reflective perspective, it emphasizes how unchanged and undisturbed the environment is. The scale of the void also encourages consideration of how the universe changes over time. Although the region is extreme by current standards, it represents a trend that becomes more significant as the universe ages. Expansion will continue to stretch space. Voids will become larger. Dense regions will become more isolated. Over long periods, the cosmic web will thin out. The distribution of galaxies will shift toward greater separation. Regions like the giant void show what this future might look like. They give a glimpse of conditions that, far into the future, may characterize much of the universe as expansion accelerates. Within this environment, the relationship between matter and space shows how cosmic evolution progresses. Dense regions have the ability to hold together. Voids show the opposite trend. Their gravitational pull is weak compared to surrounding clusters. Expansion dominates their behavior. This makes them sensitive indicators of how the universe responds to the balance between gravity and dark energy. The giant void demonstrates how a region that starts with slightly lower density becomes a place where expansion takes over early, shaping the region for billions of years. Imagining movement through the void highlights the slow but ongoing processes that define such a region. The absence of frequent interactions means that nothing interrupts the gradual stretching of space. A galaxy moving within the void experiences little to change its path. This contributes to the long-term calmness of the environment. The faint filaments near the boundaries mark the limits of this calmness, showing where matter begins to gather once more. These boundaries reinforce the sense of transition between environments, illustrating how the cosmic web shifts gradually from emptiness to structure. Considering the void's boundaries helps contextualize the region. Although the interior contains only a few galaxies, the edges display the thin threads of the cosmic web that remain. These filaments show that the void is not an isolated bubble but part of an interconnected network. They represent the points where matter resisted the outward flow, creating the framework of the web. Drifting toward a boundary reveals how density increases gradually rather than abruptly. The transition reflects how gravitational forces shape the universe over vast distances, producing environments that shift smoothly from one state to another. The flow of matter around the void offers a way to understand these transitions more deeply. Galaxies near the boundary often move outward, while also being drawn toward denser regions beyond. These flows highlight how the void interacts with its surroundings. The outward motion results from the underdensity, while the inward pull reflects the influence of distant clusters. Together, these forces create complex patterns that reveal the gravitational landscape. Following these flows provides insight into how the void continues to evolve. They also illustrate how matter responds to differences in density across large distances. Stepping back from the technical aspects of these flows, it becomes clear that they represent the natural redistribution of matter that continues throughout the universe. The void's role in this redistribution is subtle but persistent. It influences how matter moves, how galaxies evolve, and how light travels. These influences might be difficult to observe in day-to-day terms, but over billions of years they shape the cosmic environment. Recognizing these influences helps clarify how structure forms and how it changes over time. One feature that stands out when imagining this region is its duration. The void has existed for billions of years, formed slowly as matter flowed away and expansion stretched the space inside it. This long history gives it a different kind of permanence. Even though it evolves, its evolution is slow. The galaxies inside it drift quietly. The boundaries shift gently. The overall structure remains stable, relative to the rapid changes seen in dense regions. This stability provides a way to contemplate the universe on scales far beyond those of human lifetimes, or even galactic timescales. The stability also affects the region's temperature and energy distribution. With few sources of radiation, the void maintains a cooler environment. Gas inside it stays diffuse and cold. Stars within the scattered galaxies illuminate only small parts of the region. These conditions mirror the long-term direction of cosmic history, as star formation slows and galaxies exhaust their gas supplies. The void becomes a model for understanding how the universe might appear when active processes diminish. It shows how matter behaves when energy sources grow rare and interactions decrease. Although a void is defined by the absence of matter, its existence highlights the structure that surrounds it. The thin filaments and massive clusters beyond its boundaries demonstrate the contrast between underdense and overdense regions. This contrast is essential for understanding the universe's architecture. It shows how matter gathers into structures while leaving behind large empty regions. The existence of a void as large as the giant void emphasizes how widely these conditions can vary. It also shows how initial fluctuations in density can lead to long-term differences in structure. Imagining a continued drift through the void emphasizes how constant the expansion appears. Distances increase steadily. Light from distant galaxies becomes dimmer as space stretches. The few nearby galaxies grow fainter as they recede. Over long periods, these processes will become more prominent. The void provides a preview of how these changes manifest on extreme scales. Observing the galaxies inside the void offers a direct way to study the impact of expansion on isolated systems. It demonstrates how cosmic acceleration influences environments where gravitational interactions are weak. Reflecting on how the void formed provides another perspective. Its existence points to the early fluctuations that seeded the cosmic web. Those fluctuations were small, but their influence endured. The void represents a region where those fluctuations favoured underdensity. Over billions of years, gravity amplified this condition, drawing matter away and deepening the emptiness. This long-term development shows how even slight differences in early conditions can lead to considerable differences in modern structure. The void offers an example of how sensitive the universe is to its initial state. Drifting across such distances encourages consideration of how many regions of the universe remain unobserved. The observable universe is limited by the speed of light and the age of the cosmos, but beyond this limit, similar voids may exist, extending across areas that current instruments cannot reach. The giant void, though large, might be only one example among many. As telescopes improve, more voids may be found, revealing patterns that expand our understanding of how widespread these underdensities are. The possibility of discovering even larger structures underscores how much of the universe remains unknown. Studying voids also helps refine the boundaries of cosmological models. By understanding how extreme underdensities behave, researchers test predictions about dark matter, dark energy, and the growth of structure. The giant void provides a valuable benchmark for these tests. It demonstrates how models apply to rare structures. It highlights areas where predictions align with observations and areas where uncertainties remain. These comparisons help identify which parts of cosmology require further refinement. They also show how well the models describe the large-scale universe. Observing the void does not diminish the role of dense regions. Instead, it clarifies how these regions fit within the broader structure. Dense clusters represent places where matter collected, offering sites for rapid evolution. Voids represent the opposite trend. Together they create a balanced picture of how matter distributes itself across space. The contrast between these environments remains a key part of understanding cosmic evolution. Drifting through the void helps reveal how these contrasting regions work together to form the cosmic web. By the time the journey through this region has been fully considered, it becomes clear that the void reveals how the universe behaves over large distances and long timescales. Its emptiness highlights the influence of expansion. Its shape reflects early fluctuations. Its galaxies reveal how isolation shapes development. Its boundaries show how matter organizes itself. These features together create a perspective that complements the study of dense regions, offering a fuller understanding of the universe's large-scale behavior. The giant void stands as one of the clearest demonstrations of how the universe evolves, when gravity and expansion act over immense periods. Moving through it builds a picture of conditions that shape much of the cosmos, emphasizing how matter and space interact across vast distances. It also reveals how the universe may continue to change, showing trends that will grow more pronounced as expansion accelerates further